as for now, shall we? I mean, should we take a look at this? Is it time? Is everyone ready? Does everyone feel mentally and emotionally prepared for this one? I hope so. All right, so let's dive in now. Strings rearrangement. So we're given an array of equal length strings. We want to check if it's going to be possible to rearrange these strings in such a way that once we've rearranged them, basically every string in the array will differ by only one character, and exactly one character. The use of the word exactly here is a really important one because it can't be like the same string, right? That's an important thing. It has to differ by one. Okay, so this is a really neat problem. And I do have to say, the first time I looked at this, I really didn't have an appreciation of just how deep this goes and how interesting the underlying challenge here is. So we're hopefully going to see that today. But first, I mean, basically what we're trying to say is, is there an arrangement here? Is there a way we could just rearrange these things in the array such that, it'll flow so that from each one to the next, there's only going to be one different character between each string. So for example, we'll start with the second example actually. In this case, we're going to say true. It can be rearranged because if we arrange it like this, we've got A, B, B. Okay, so these differ by one character, these differ by one character. It's what we're looking for. Great. But you'll notice we did have to rearrange it in order to get that. Okay, whereas this one, even if we went through all the possible rearrangements, it's not going to work. And the reason is because this middle one, B, is... It doesn't have another string. Like none of the other strings in the array differ by one character with BBB. They both differ or wait, sorry, this one does. I guess it's actually this one that's the problem. ABA differs by more than one character with each of the other two. Sorry about that. Anyway, the point is, if we want to change ABA to BBB, we'd have to change both of the A's to B's. If we want to change ABA to BAB, we'd have to change all the letters. So that's no good. I mean, yeah, we're not going to be able to do it no matter how we rearrange it. Now, speaking of rearranging, this might remind you of something we've technically done before, but the way I want to look at this, at least the first time around, is I want to basically take all the possible rearrangements of this array. I basically want to reorder all the elements in all the possible ways while still using all of the elements. So what are we talking about here? Well, I guess we're talking about permutations, right? So like I said, we have technically done permutations before. We've looked at an algorithm where we found all the permutations, and it was a little bit complicated. So I actually want to start by first trying to get an idea of how we're actually going to do these permutations. So let's start on the whiteboard over here, and let's just take like a really basic string. I'll just do 1, 2, 3. Okay, so you can think of that as the string 1, 2, 3 as opposed to the number 1, 2, 3, just because of the way we're going to pick it apart. Maybe it's even an array 1, 2, 3. Actually, probably, yeah, best that it is an array, right? Because that's the thing that we want to be rearranging. It's not the strings in this case. And actually, okay, that's a good point, because the last time we looked at permutations, we were doing permutations of strings. This time we're doing permutations of the whole array. We don't want to touch the strings on the inside. We don't want to reorder these. Okay, so basically we'll have our array 1, 2, 3. And then basically we want to look at all the possibilities here. So the way we do this is we say, okay, first let's start with the possibilities that start with a 1. Okay, so we'll say, look at the permutations that start with just 1. And then from there, well, you can have a 1 and then all the possible rearrangements of the remaining elements, right? So basically we pick out that 1, and then what we're dealing with after that is we want to know how to place these two, okay? So it's kind of like, we could say that we're sort of like starting a new array, which is going to represent each of the, well, it's going to represent our permutations is the idea. And then basically we're going to get the rest of our elements from here. Now, the way we're going to deal with this next part is exactly the same way. So we're going to say, okay, so then let's do the same thing here. We'll run the same loop on this. We're going to do a recursive algorithm where now we'll say, okay, we'll go with the 2. And I'll keep it the same color. So now our array has a 1 and a 2 in it. And what's remaining? Well, just the 3. Okay, so then that means, well, not much else we can do with this. This is going to result in the array 1, 2, 3. Okay, and that's all that we could have done with that one. So we've kind of closed the loop on this stuff over here. But then there's also this other possibility here. What if we were to use 3 instead? So going back to this, we have the array that contained 1. Now we're going to say, instead of putting the 2 in there, now let's deal with the 3. And what's left over at that point is just the 2. So then from there, same sort of thing, we keep the algorithm running, and basically we'll keep it running until we get to something that's long enough that we can stop. So in other words, something that's as long as the original array. So you'll notice we're starting to produce some permutations. We've got 1, 2, 3, we've got 1, 3, 2. Now at this point, there are no more possibilities in this array here. We've exhausted all of our options. So we're going to go back to the original and we'll say, oh, okay, well, what if we had started with one that was 2 in the beginning, and then the possibilities for the other ones would be 1 and 3. So we're basically just like taking out the one that we use. Okay, and then basically the idea is we would continue this, we do the same thing, but you'll notice we're sort of doing the same kind of loop through each of these at every level. So we look at 1, 2, 3, start with 1, and then basically do everything you can with that 1, which means we'll start with 2 and then do everything we can with that. And then once that's over, we'll go to the 3. Once that's over, we go back to this one. So it's going to be recursive. We're basically, we're getting all the way down to an actual permutation before we go back. Well, actually, we're getting all the possible permutations that start with 1, and then we go back to the array and say, okay, what if we wanted to start with 2? Okay, so that's basically going to be our approach to this. We're going to generate all the permutations, and then we're going to look to see which of those permutations has the property we're looking for, if any of them. So we're going to say function, and maybe we'll make it like get permutations of an array. Okay, and I'll say let full length, I guess, be assigned the value of array dot length. Okay, and in fact, that's not going to change, so maybe it should be a constant. Cool. All right, and then we're going to say let sequence be assigned the value of an empty array, and we'll say let permutations be assigned the value of also this empty array. Okay, so if you're wondering what is all this stuff, well, first of all, we need to know the full length to know when to stop, to say, oh yeah, you've got 3 things, this had 3 things, we're good. We need sequence, because sequence is going to be the thing that we're sort of building up and then breaking back down. So basically, and okay, this isn't actually something I really mentioned, but once we get to a full sequence, and sequence, by the way, is like this, it's the array that we're building up here. Once we get to the end here, then we're going to go back to the previous one, right? So this was 1, 2, and then we say, oh, okay, well, we covered all the possibilities that have a 2 here, so let's pop that 2 back out, and we're just left with the 1. Now let's push the 3 in there and see what we can do from there. And then, yeah, each of these guys, since that's a full-on permutation, these would be like, as soon as we realize they're a full length, they're length 3 in this case, then those would be in the permutations array, something like that. Anyway, that's the idea. So permutations is the thing that's going to hold each of these arrays, and then sequence is going to be these things. So sequence is going to change a lot. Permutations, it's only going to change in the sense that we're going to insert more things into it. We're going to push more elements into it. But sequence is actually going to be a little more dynamic and interesting. It's going to be changing its value on the fly, or its contents on the fly, I should say. Okay, so now we need to do something with this. So we're actually going to have a function within a function, and this is going to be the recursive part of it. So I'm just going to use A because we already have R up there, but this is going to be an array. Now the idea is that, oh, not this again. We want to do this. We want to call this interior function. How did I fix this last time? Something like that, was it? Anyway, at the end of this, we're going to return permutations once it's all filled up. That's the idea. Okay, so this is going to be, get permutations here is going to be sort of like the thing that starts it off and lays down the arrays that it's going to fill up. And then permute is the function that's actually going to be calling a bunch of times. So that's the thing, like, you know, when we're looping through these and saying, okay, maybe it's 1, maybe it's 2. That's what permute is going to be doing. So it's the recursive part. It's going to be, well, happening a lot. Okay, so what's going to happen in here? Well, since we need to look at all the possibilities, all the possible elements, we'll say for let I be assigned the value of 0, I is less than a dot length. Notice we're not using full length here because a might not be the full array. It's going to start out as the full array because we're doing permute with r, but later on, like, you know, we start with this array, right? And then as soon as we take the 1 out, now we're kind of left with like this array. And then after we take the 2 out, let's say, we're left with this array. Okay, so like these ones here, these are A. Whereas like this one here was more like R. It was the one that we started with. And it will be A for the first time around. Anyway, the idea is that we want to go through each of the elements and we'll say let str be assigned the value of a at I, so the string at that index. And you might be thinking, oh, well, couldn't you just done like for let str of a? And well, there's a reason why I don't want to do that. And the reason is because I'm going to be using I for another purpose a little bit later on. So what are we going to do with this? Well, first we're going to say sequence.push str, right? So I'm saying str is in string, but really what I mean is just the element, whatever it is. In this case, it is a string, but in the example we looked at over here, just for the sake of simplicity, we just used 1, 2, and 3. So we just used integer values there. But the main thing is that sequence is getting string pushed into it. So like in this case, we said, all right, start with the 1, and then that's, you know, sequence has 1 in it now. Then after that, once we resolved all that, sequence would just have 2 in it. Okay, I should probably mention, since it's recursive, basically sequence is going to get filled up. Like we're going to keep, like, because we have access to sequence, right? It's out here, so we're going to keep filling it up. So this is just the first, well, okay. The first time this executes, it'll just be the first string, but it will eventually get all of them. So basically what we want to ask ourselves is, well, is sequence long enough? Is sequence.length equal to full length? And if it is, then we just want to push that permutation. So actually maybe I don't want to get this getting too wide or anything like that. So we'll say permutations.push. And now it's tempting at this point to just say sequence, but I think that's going to cause some problems because we need a deep copy of this thing, right? Otherwise, we're just going to be altering sequence afterwards. So we'll just do it this way. Spread operator with our object literal here, or our array. And, you know, we could have also done dot slice, but I feel like this is maybe a little more semantic. I don't know. It's up to you. If you prefer slice, that's fine. You can use slice. Okay, so that's the if. But then we're also going to have this else. So what if it's not full? What if there's more to do with this sequence? So it's only going to be full when we get to the end here, but we might be looking at like an in-between step like this, right? So if it's not full, then we want to be doing some other stuff. What do we want to be doing? Well, specifically, we want to be calling this function again. What are we going to call it with, though? I'm wondering if I should use another variable for this. So I'll say let remaining. So this is like the remaining strings in the array, the ones we haven't used yet. So remaining is going to be an array containing, well, actually, yeah, okay, we'll do it this way first. So we'll say a.slice, which will go from 0 to I. So remember I said I was going to use this I index again. I wasn't lying. Okay, here it is. So then we want this, and we also want to spread out a.slice at I plus 1. Well, let's get a bit of extra room in there. Great. Okay, so what's going on with this? Well, first of all, I do want to mention this is absolutely equivalent to if we were to say let remaining be assigned the value of a dot slice 0 I not o 0 I dot concat a dot slice I plus 1. And actually we could get a little more detailed than that, you know, like we could say like let left part or something like that be assigned the value of a dot slice 0 I, you know, like that's the left part of it. That's just the stuff that's to the left of whoops, Freudian slip. Yeah, that's just the left part, so it's just the stuff to the left of the element that we're using in this case. And then right part would be a dot slice of I plus 1. And keep in mind, if we don't give it a second argument, it's just going to go to the end of the array there. So I is the index of the element that we're currently using, and we're saying we want to do, first of all, everything from 0, including 0, up to and not including I, and then after that, we want to take the part that comes after that, right? So basically just to the right, just after I, because I plus 1. So then we just say something like left part dot concat right part. Yeah, there we go. So what I'm trying to say with this is like this, all of this stuff here is just the same as this stuff over here. I mean, these are two different ways of writing the same thing. It's up to you, whatever you feel more comfortable with. If you have a preference, follow your heart. Okay, so I think my preference is probably to just do it like that. So maybe I should have kept the other one in a comment. Oh, well, you can rewind if you need to see it. All right, there we go. Permute with remaining. Okay, so remaining again is just going to be like after we take out the 1, remaining would be 2, 3. So that's why we're calling permute again with just 2, 3. So that's the idea, and then that's going to sort of whittle it down. Now the only problem is after we're done with this, you know, like after we've already taken out the 2 and then we take out the 3 from here, and then, you know, we're done with that. Basically, the idea is that when we move on to this one over here, where we want it to be 1, 3, well, we don't want the 2 to already be in there. So we want to clear it out. You know what I'm saying? Okay, well, when we're done with this one, when we want to go back and move on to the next one, get rid of that one. So the way we'll do that is we'll just pop it out because it's going to be the most recently added element. So sequence.pap. There we go. And let's see, is there anything left to do? Is this good? Is this going to get us all of our permutations? Let's find out. So maybe I'll just do like a return get permutations, and I'll just do like a basic example. So 1, 2, 3, I guess is a familiar one. Let's see what happens with that. Oh no. Well, that's no good. Okay, what happened here? I'm getting some nulls. I don't have the right number. There should be like 6 of these in here. So something must have gone wrong. What could it have been? Okay, so we said full length is ray.length, sequence, permutations. We've got our permute function here. Returning permutations at the end there. Yeah, what are we doing wrong here? So something like this. Okay, let's see. Am I missing anything here? Sequence.push. Yeah. And sequence.pop is like removing that one. Oh, look at this. This is like the oldest mistake in the book. I'm so sorry about this. Okay, if you guys are as oblivious as me and you don't see what's wrong with this, I was missing the other equals. Okay, I wasn't trying to say sequence.length is assign the value of full length. I was trying to say sequence.length equals full length. I was trying to ask, are these things equal to each other? Okay, so hopefully that sorted it out. Let's take a look. So that looks better. All right, great. That's giving us all 6 of the permutations we're looking for. We've got 1, 2, 3, 1, 3, 2, and those were the ones that we came up with over here. If we had continued this, you know, maybe if I had a little more space, then we would have got 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. But the main thing is these are all the permutations. This is all the possible ways we could rearrange the numbers 1, 2, and 3. Okay, so now that we see that it's working with 1, 2, and 3, let's actually see if it's working with our input here, input array, the thing they're giving us. So, bab. I'm probably not going to try to pronounce all of these, but it looks like it's working. You know, we have the same number of them. There are 3 elements. We should have 6 possible rearrangements, 3 elements again. Maybe there's one with a longer set of elements. That one's got 4, so this should be like, I guess, 24 rearrangements. It's factorial, so what about a really long one? Yeah, this should be like 120 of them. Yeah, that goes on for a while. It looks like it's probably getting all of them. Wow, that is really, really long. Okay, so I wonder if that's the longest one or... Oops. Yeah, that was probably the longest one. Okay, great. Well, I'm glad we looked at those. So it looks like our permutations are working. And importantly, it didn't time out on any of these. You know, like you notice it was able to get the permutations of even if the length was 5. So that's good. It's not timing out. Oh, hey Firefly. Glad you've been enjoying it. That's cool. Thanks for stopping by. Let me know if you have any questions, by the way. So, where were we? We've got our get permutations up here. Okay, so instead of returning get permutations, maybe I'll say something like let sequences. Let sequences be assigned the value of get permutations. But actually, I'm noticing before we go any further, there's another function we should be doing here, and it's so important that it really should be at the top. And the function is going to be called differ by 1, and it's going to take in 2 strings. Yeah, those are what we're trying to compare, right? String 1, string 2, and then basically we just want to compare, like, do they differ by only 1? Do they only have 1 character that's different? So I'll say let mismatches be assigned the value of 0, and we're going to count the mismatches. So we'll do a for loop. We'll say for let I is assigned the value 0, I is less than string 1 dot length I plus plus, and let's see. Basically, we want to say if string 1 and I is not equal to string 2 and I. And that means we have a mismatch. So mismatches plus plus. Okay, and if we get to the end and it turns out, well, I guess basically this is what we want to say. Return the Boolean mismatches equals 1. That's really what we're after, right? We're trying to see, is there going to be exactly one of these things, right? That's what we want, right? Exactly 1. Okay, so yeah, differ by 1. Let's see if that works. Maybe we'll just test that and then we'll go on from there. So return differ by 1, and we need 2 strings here that differ by 1 character. So maybe like cats and bats. Let's try that. So we should get true for that one. True, okay, that's good. And now let's try cats and bots. We'll see if we get, no, we get false for that one. So that's good because they do differ by more than 1 character. So great, that function's working. Our permutation function is working. So all the pieces that we need to get this going are up and running. Now we really just have to say, looking at our sequences here, we'll do a loop on them and we'll say for let sequence of sequences. Okay, so a couple things I want to say about this one. I am now using the of loop because I don't intend to use the index for anything. All I need to know is what does the sequence look like. The other thing I want to say is you might be looking at this and thinking, yeah, but use sequence up here. Isn't it going to be a problem that you're using the same name for your variable? And the answer is no, it's not going to be a problem for a couple reasons. Both of them have to do with scope. So regardless, I mean, this sequence was defined within the function get permutations. This sequence is being defined within the function stringsRearrangement. But furthermore, since I'm using a let instead of a var, that means that this is going to be block scoped. So in other words, the scope of sequence, this sequence, is not actually strings rearrangement. It's this for loop. Like if I asked, out here, like, hey, can you return sequence? Then it would be like, what are you talking about? And I guess I'll just say, do nothing for now. Yeah, it would be like reference error. I don't know what sequence means. What are you talking about? Whereas if we talk about sequence in here, it'd be like, yeah, no problem. Makes sense. Okay, so we don't want to actually do nothing in here. What we want to do is we want to check if our sequence is as it should be, right? So how are we going to do that? Well, basically we want to loop through these. So for let, I guess I will use the index this time, I is less than sequence dot length I plus plus. You might be asking, why am I using a 1 here? Well, and actually the fact that I am using a 1 here is the reason why I'm not doing another of loop, okay? Because I need to change the indices on this one. Actually, there's another reason. So basically, yeah, what we want to do is this. We want to say if differ by 1, and we want to say sequence. Actually, you know what? I kind of feel like using a few more variables for this. I don't know why, but let this one be assigned the value of sequence at I. And then let previous one be assigned the value of sequence at I minus 1. Because we need to compare the two adjacent ones, right? We need to compare like our ABBA to our BBB. And so one of them is going to be this one, the other one's going to be the previous one. And that's the reason why I started I at 1 instead of at 0, because if it was at 0, I minus 1 would be out of bounds. Okay, so we've got this one, we've got previous one, and basically what we want to say is if differ by 1, this one, this one, and previous one, then what do we want to do? Well, actually, that's like that would be good, right? That's what we want. So let's say if it doesn't differ by 1, then we'll say like the deal's off, break. Get right out of this loop. But before you do, let's just say, actually, yeah, great. Possible is assigned the value of false. What's possible? Well, it's the thing I didn't yet declare up here. So we kind of have like, let's see, return possible. No. We want to say if possible, then return true, because that means we found it, right? We found the 1. And then after that, if we don't find the 1, then we'll say false. Okay, let's get a bit of a breakdown on how this is working. So we've got all of our sequences. Those are being generated by get permutations. So that'll be like, all the possible rearrangements of these. And then for each of those sequences, it's going to go through them one at a time, and it's going to compare adjacent elements. So it's going to compare this one to that one, and then it's going to compare this one to that one. And we kind of have this like innocent until proven guilty style of looking at this, where we're saying, well, right off the bat, you're a new sequence. I haven't met you before. I don't know anything about you yet. I'm going to say, believe in yourself. Maybe you're the one we're looking for. Maybe it's possible. Maybe you have the potential to be the sequence in which every string differs by exactly 1 character to the previous string. But as it's going through the loop, if it finds that there's even one set of adjacent strings that do not differ by 1, then we'll say, sorry, no longer possible. You are ineligible to be the one we're looking for. And at that point, we don't want to waste our time going any further through this loop, because if we find like either a mismatch, like a more than one mismatch pair, or like maybe a 0 mismatch pair, we'll say, oh, okay, not possible. Don't waste your time checking the rest of it. Break. Okay. And then at the end of that, we'll say, if possible, return true. And this return true, keep in mind, even though, like I was saying, like all these lets are scoped to just this block here, despite that, our return statement is still corresponding to this large outer function, strings rearrangement. So that return is going to return like the final value, like that is our answer. That's what like this down here is gonna get back. So let's run the tests on that one. Let's see if this is working. Oh, look at that. It's passing all the sample tests. This is very exciting. Okay, so I guess there's not much left to do at this point. I could probably throw some comments in there, but I gotta say, I'm pretty anxious to find out if it's gonna pass the hidden tests. So Let's run it. Oh my. Okay, so you can probably hear my excitement building there. I'm actually kind of surprised that worked. Oh, and look at that, you gotta love that. Extra 5,000 coins for the pocketbook. Okay, that's awesome. I'm actually very surprised though, I do have to say, because I wasn't really expecting this to work that well, because just like this get permutations thing. So here we're generating all the permutations. I'm having trouble with that word. Generate all the permutations. And this is going to be, I'm pretty sure this would be like big O of n factorial, where the factorial, the n is like the length of the input array. Maybe I'll say that, where n is length of input array. Okay, so just this function here, right? Just the permutations one, that's going to be big O of n factorial. So we do that, we generate all of those. And then for each of those, for each one of these things that we generate, we're going through this. And so this is going to be, well, I guess this is like the length of the sequence, right? So that would be, yeah, not, well, actually, hold on. That would be, because there's a loop in here that goes through the length of the string. And then this is going through each of the, this is going through each of the sequences. Like this is going through the array for each of the sequences. And then this up here is going through each of the strings. Okay, so this is, compare the strings, and this is going to be big O of, let's say, m, right? Where m is the length of each string. And actually something I didn't mention before is like I do have to say differ by one. This function is actually, it's like very specified. It's specialized for this particular scenario, specifically this part of it here. The fact that we know that these are going to be equal length strings. Because if we didn't know that, then I would have to say return mismatches equals 1 and string one dot length equals string 2 dot length. But we already know they're going to be equal length, so I don't need to bother checking that. I mean, why waste our resource, our computation time on something that's already known in the problem? Okay, so big O of m, and we're doing that how many times? Well, we're doing that, I guess, n many times. This thing is going to be big O of n. So I think the whole thing, this whole algorithm, which I guess we're going to archive it because we're done with it. It worked, right? So we're going to get rid of that. And I'll say, I think this is big O of n. That should be a comment. Very colorful otherwise. Okay, I think this is big O of n factorial times n times m. That's what I think it is. But somehow it worked. Yay. Okay, so I think that's what it is, which is like, by the way, horrible. Just like beyond horrible. Just like really, really, really bad. Like that's bad. So I'm surprised it worked. Anyway, probably the reason is because of these constraints here. Notice like the length of the strings can't be very long, only 15. And the length of the array, even shorter. It can only be as many as 10. So I think that's probably the reason why this worked. So in some ways, I'm pleased about that. In other ways, I have to be honest, I'm almost a little disappointed because there's a better way. There's definitely a better way. In fact, why don't we take a look at the comments for a second here, and let's just maybe go to like, I don't know, maybe the 4th page or something like that. Maybe we'll find some wisdom in. Oh, take a look at this. So we've got a user here who's talking about Hamiltonian paths. So other users have pointed out this is fundamentally a problem of finding Hamiltonian paths. I found this page helpful in developing a dynamic programming algorithm over a bitmask in big O of 2 to the n times n squared. Well, I have to say 2 to the n times n squared seems a lot better than whatever we had there, n times n factorial times m. So, okay. Sounds good. Maybe we should take a look at that page. What do you think? I'll load it up in a new tab here. And yeah, it's ready. Let's take a look at that. So, Hamiltonian path. Well, to get the definition from here anyway, it says a Hamiltonian path is a path in a directed or undirected graph that visits each vertex exactly once. So I'm looking at this, and I mean, I think I understand what that's saying, right? It's a path in a directed or undirected graph that visits each vertex exactly once. I guess this would be an example of an undirected graph. Oh, and by the way, if you're not all that familiar with graph theory, you might find this a bit strange, a bit like not what you're expecting, because I know before I got into some of the like heavier university maths courses, I was sort of under the impression that a graph was like, you know, Cartesian plane kind of thing, like, oh, and profit's going up. Anyway, the point is, this wouldn't have struck me as an example of a graph. Anyway, this is a graph. This, I guess, is a graph where there isn't a Hamiltonian path because, like, you know, start anywhere, you're not going to be able to get through all of these. You know, now we can't get to the 3. And we're not allowed to retrace our steps because exactly once. Okay, so that's not going to work. But if we modified it and made it kind of more like a coat hanger shape, then it would work. In fact, this one works in 2 ways. We could even burn one of the bridges here, right? We could take away that edge and it would still be fine. Like, we could still traverse a Hamiltonian path with that. Okay. So then I'm looking at this and I'm thinking, well, great. You know, that's nice. That's good to know. Oh, by the way, this is hackerearth.com in case anyone's wondering. So I'm looking at this, I'm thinking, yeah, okay, cool. You know, that's neat, but how's that relevant to this? Or like, is this guy answering, did this guy put the comment in the wrong challenge or something like that? Like, is this really relevant to this thing over here? Oh, not solutions, I want a description. Is this, like, does this seem like a graph? Does this seem like a Hamiltonian path kind of thing? And I thought, no, not really. So then I thought about it a little more and I realized, check it out. Just a bit of vocabulary here. When we're talking about a graph, just in case you're wondering, each of the circles here, like all of these guys, these are called nodes, usually. Nodes. That's what I'm going to be calling them anyway. Nodes. And the things that are connecting them, so like these things here, these are usually called edges, which is really barely visible. I don't know why I chose that butter popcorn color for that. But anyway, these are called edges, which again, like it probably seems weird. Like we think of a graph as being something different. We think of an edge as being something different. These are words that we've seen before in other contexts to mean something else. And so I found that kind of troubling when I first encountered this idea of graphs, but hey, you get used to it. All right, so that's what we want to do. We want to find a way, I guess, of looking at this problem in such a way that maybe resembles a graph. And then from there, we can talk about what it means to have a Hamiltonian path and all that. So for now, I guess we'll just use this space right here, and let's get a pretty sick color in here. Yeah, Dusty Rose, that's a nice one. Oh, okay. So looking at this first one here, we've got A, B, A. And then we've got B, 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 and then we've got B, A, B over here. So these are the 3 elements here. I'll even give them indices. I'll say this one is 0, this one is 1, and this one is 2. And then here, let's make them proper nodes by encircling them. Okay, great. And now we want to talk about what it means to have an edge in this situation. So, any suggestions on colors? What would go good with these? Maybe orange? We'll go with orange. Okay, so what does it mean to have an edge? Well, it means you differ by exactly one. You know, it means you would pass that function that we wrote downstairs. So to have an edge is to differ by exactly one. That's the idea. Okay, cool. So then notice, like this is the only edge here, right? Because these two wouldn't be connected. These two wouldn't be connected because they don't differ by just one character. Like they have two different characters. These have three different characters. So it's not going to have an edge. So this is the only edge, which means, yeah, no possible way we could trace out a Hamiltonian path here. It's just not going to work. All right, cool. So then let's clear that for a minute. Let's choose some new colors, 'cause that's always fun. Oh yeah, this looks like a nice green. Minty. Okay, so now let's look at this one over here, and we'll say we've got AB, we've got BB, and we've got AA. And so what we're going to do with these is, first of all, we'll get the indices 0, 1, 2. Yeah, lavender and mint green. That's a winning combo right there. So we'll circle those up. Oh, now we need a third color. I didn't think I had this far. Oh, I hope I don't mess this up. We're going to try this electric pink thing. So AB and BB differ by one character. BB and AA do not differ by one character. And AB and AA do differ by one character, which means that in this example, we can definitely trace a Hamiltonian path. Okay, that's what it would look like. And there's no undo button for this page marker app, which is too bad. So that's why this one passes. It does have a Hamiltonian path. Okay, cool. So now we can sort of see how this problem corresponds to graphs. You know, we can sort of look at this as a graph problem. It's still kind of weird to think of it that way because, you know, that's not really, it doesn't look like a graph, I guess is what I'm trying to say when we first look at it. But it's a graph. So we're going to write a new algorithm which is going to convert it to a graph. That's basically what it's going to do. So we're going to say that each of our strings here is going to be considered a node. And actually, let me take a step back for a minute, because it's not really that each of the strings is going to be a node. It's that each of the indices is going to be considered a node. That's a little simpler to work with. We could use the strings, but the indices, yeah, easier to work with. So 0, 1, and 2 instead of all of these things. Okay, so we know what the nodes are going to be. The nodes are just going to be the indices. So like 0, 1, and 2, or like 0, 1, 2, 3, 4, like depending on how many things there are in the array, right? But that's our nodes, so we don't need to worry about those. What we do need to worry about is edges, because it's not clear yet what the edges are going to look like. Okay, so then for the edges, keep in mind having an edge means that they differ by exactly one character, which is why I'm going to go ahead and grab one of these functions we had from down here. This one, differ by one. Let's just get that back up in the mix. I mean, we could rewrite it, but yeah, copy and paste works just as well. We're reusing our code. So we've got our edges currently empty, nothing in the edges. What we want to do is basically, we want edges to be a matrix, I guess. Well, okay, no, it's maybe inaccurate to call it a matrix, but it's going to be a two-dimensional array in the sense that it's going to be an array containing arrays. And the way it's going to work is for each element of the array. So actually, let me delete that for just a sec. What we want is basically, I guess using this one as an example, what we want is an array that tells us, okay, for each, I guess I'll do it like this. So I'll say this is the larger array, and then there's going to be smaller arrays within it. So for the first one, the 0th array, it's just going to contain all the indices of the connected nodes. So like, again, looking at this one, AB is connected to BB. In other words, 0 and 1 would have an edge. AB and AA also have an edge. So the 0th element within this larger array, the edges array, the 0th element contains indices 1 and 2 because those are the indices of the strings you can reach or that differ by 1 that have an edge with element 0. Okay, so the 0 is coming from the index of edges, and then the 1 and 2 are the ones that are connected to that. And then from there, well, BB is connected to AB, so this next one is going to have 0. BB is not connected to AA, so that's it, just a 0. And then for this last one, again, it has an edge with the first one, not with the, with the 0th one, not with the first one. So there we go. That's what it's going to look like, and that will be the end of the edges array. So that's basically how we're going to do it. Now, look, there are other ways we could do this, right? Like we could actually make it more of a proper graph by doing something a little more object oriented and saying, you know, node, edge, and like defining those kinds of things. And who knows, maybe that would actually make it easier to find our Hamiltonian paths. I don't know. But I'm kind of getting the feeling like this is going to be a long video to begin with. So I probably don't want to make it any longer than it's already going to be. But, you know, look, if there's interest, if anyone wants to see that, if anyone wants to see like a more object-oriented approach, then yeah, we can look at that maybe later. But for now, I'll say edges is just going to start as this empty array. Okay, and then we're going to fill it up. So we're going to say for let I be assigned the value of 0, I is less than input array dot length. Because remember, we're going through each of these nodes and we're saying, hey, who are you connected to? Who are you connected to? And then from there, we'll say, okay, we're going to start a row. Maybe there's a better, I don't know. I'm wondering if there's a better word, like a better variable name for what I'm calling row here. But anyway, just to show what's going to happen with that, we're going to push the row into edges once we're done filling up the row. So what's the row going to look like? Well, basically, we're just going to go through the remaining elements. So J is also going to start at 0. It's also going to go all the way to input array.length -1, because it has to be strictly less than it. And then what we're going to do in here is we're going to say, well, first of all, if this is a different node that we're talking about, so I can't be equal to J because, you know, well, I guess I don't really need to check this because if I was J, then they definitely wouldn't be differing by 1, but oh well. And differ by 1 with an argument that's going to be a little bit complicated. Input array at I, comma, input array at J. Yeah. And I'm only now realizing that like the I not equals J is kind of the only reason we're, you know, using the indices, like why we're not just using a for of loop. So maybe we should do it that way. I don't know. First, let's just see if this is working. So let's return edges. We'll run that and we'll see if we get sort of, you know, something close to what we're expecting. Oh no, syntax error. Line 20, this. Oh yeah, what do we want to do if that's true? Sorry, we want to say row.push J, because that means there is an edge between I and J. Okay, so now let's run the tests on that. Sorry about that. Okay, so we were looking at the second one, right? And we were finding that it should have been something like, what was it? It was an array containing 1, 2, followed by an array containing 0, followed by another array containing 0. So, would you look at that? Just what I've been dreaming of. That's nice to see. Okay, so, awesome. Edges is working. Now, oh, yeah, silly me. Of course there is a reason why we don't want to be using a for of loop. It's because of this. We need to push J. Okay, so I guess it's because I hadn't typed that in yet. That's why I was having second thoughts. But okay, this is good. This is basically graphifying it, right? This is taking the whole problem and turning it into a graph. Cool. So now we just need to tell if there's a Hamiltonian path on this graph. That's all it's going to take, right? The problem is that it's not all that easy. I mean, there are a few ways to do it, but specifically the way we want to do it you know, because we got this comment from this this unknown user over here that said something about, yeah, dynamic programming algorithm over a bitmask. So we're going to take this opportunity to take a bit of a step back from what we're doing. Okay, we've got this all set up. We have this in the form of a graph, and I do want to do this dynamic programming algorithm over a bitmask, but I just have two issues with this. Number one, what's dynamic programming? We haven't really talked about it yet. And number two, what's a bitmask? We haven't really talked about it yet. So maybe we'll talk about each of those things first, and then we'll come back to this. So we're going to step away from this problem for just a minute. I'm wondering which one we should do first, the dynamic programming or the bitmask. I don't know. Anyone have any suggestions? Is there one that that any of the viewers would like to start with? If so, let me know. I would say probably the dynamic programming is going to be a little tougher, a little conceptually more difficult, and the bitmask is going to take a while to explain, but it'll be a bit simpler, especially if you're familiar with binary numbers. So I don't know, maybe that's the better one to start with. Yeah, because we want the dynamic to be sort of like fresh in mind when we redirect our attention back to this problem here. So okay, we'll start with the bitmask stuff. So when I think bitmask, I think of bits. And when I think of bits, I think of binary numbers, like 0 and 1. Anyway, the point is we're going to go back to the drawing board over here. We're going to clear what we have because this is, well, it's not what we're doing anymore. We're not actually finding all the permutations, which is nice. That's why we're going to have a more efficient algorithm here. So let's see. Okay, we need to talk about bitwise operators. We need to talk about binary. So when we're talking about binary, let's come up with a couple of binary numbers. So let's say something like a 1, 0, 0, 1, 0, 1. Yeah. And I'm trying to sort of space out the numbers a little bit here. I didn't do such a great job, but anyway. You'll find out why that was in just a minute. So this is a binary number. I guess let's start with the basics. Binary is, it's a number system. It's just a base 2 number system. So when we think of like a decimal number, like something like 759, then basically the idea is that when we're looking at this thing, the 9 here is like the ones column, you know, the 5 is in the tens column, the 7 is in the hundreds column. But the way to think about it is basically this would be 10 to the power of 0, which is 1. This represents 10 to the power of 1, which is 10. This is 10 to the power of 2, which is 100, right? So basically this number, this whole thing could be expressed as like 7 times 10 to the power of 2 plus 5 times 10 to the power of 1 plus 9 times 10 to the power of 0. But this here is kind of complicated to write out. It's, you know, this isn't easily readable or writable. So that's why we just use this most of the time, 759. We know by looking at it, because we're so used to base 10 number systems, that, that this is going to be the hundreds, that's going to be the tens, that's going to be the ones. Okay, so, and like, you know, not a coincidence that this is a 10 here and we're calling it a base 10 number system. Okay, so that's a decimal number, and we call it a decimal number because like the DEC there stands for 10, right? In, I don't know, Latin or something. Anyway, the point is we want to be looking at binary, and in binary, the BI stands for 2. So in case you haven't guessed it, binary is a base 2 number system. Okay, so this 759 here, the thing I wanted to say about it is if we're going from the ones to the tens, that means, you know, each digit could be like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have to have 10 digits. In binary, since it's a base 2 number system, we don't have to have 10 digits. We only need 2 digits. That's why it's all zeros and ones. So this spot is for 2 to the power 0, which is 1. This is for 2 to the power of 1. This one's for 2 to the power of 2. This is for 2 to the power of 3. This is for 2 to the power of 4. And this is for 2 to the power of 5. And we'll switch colors again just to write in the actual numbers for these. So this would be 32. All right, I'm kind of on a cool diagonal. This one would be 16. This would be 8. This would be 4. And this would be 2. And this would be 1. So instead of having like the ones, the tens, and the hundreds, instead of that, we have the ones, the twos, the fours, the eights, the 16s, and the 32s. So if we want to know what this number would look like as a decimal number, well, basically this number is just 1 times 2 to the power of 5, or 1 times 32, plus 0 times 2 to the power of 4, plus 0 times 2 to the power of 3, plus 1 times 2 to the power of 2. I'm not writing in the zeros because, you know, they're nothing. They have no value. 0 times 2 to the power of 1, 1 times 2 to the power of 0. So in other words, it's going to be equal to 32 plus 4 plus 1. So this is 37. This in binary, as a binary number, this is exactly equivalent to the decimal number 37. Okay, so 37 in decimal is 37. 37 in binary is 100101. And in case you're not convinced, I can demonstrate. So there's this nice built-in for JavaScript, and we've actually used this before, where we've said something like return, actually, let me say, let num be assigned the value of 37. And then we'll say return num.toString. Right, we've done that before, and it basically just turns this into a string. So it puts quotation marks around it. That's basically it, right? And there we go. Yeah, just the string that looks like the decimal number 37. The nice thing about this is we can actually pop in an argument for toString. And the argument I'm going to use is 2 because this is going to give us the representation of the number 37 as a binary number. 100101. Hey, that sounds familiar. Oh yeah, it's this. Okay, great. So that's a nice little built-in, and this works for other things too. You know, if you wanted like a base 3 number, you could do that, and that's kind of different. You could have a base 16 number if you wanted it in hexadecimal. There are lots of different number systems. Oh, that one's not too interesting. Let's say, what should we say? Like 99. Let's say 99 in base 16. I have a feeling that's going to be more interesting. No, it's not. 199. Let's try that one in base 16. Yeah, C7. There we go. Okay, so that's a little more interesting. And then we could also do something like this. We could say like let str be assigned the value of 100101, and we want to return parseInt of string. And of course, if we just do a parseInt, then it's going to say, yeah, it's, what would that be, 100,101? But we can specify the base as our second argument for parseInt. So we tell it the thing that we're trying to convert, and we tell it the base, and now it says, yeah, that's the number 37. Cool. All right, so, and you know, again, that could be any base we want. So I can make this like a hexadecimal number, and it'll convert that into a base 10 number, which is very large. Okay, great. So we'll forget about that, or better yet, we'll remember that, but we'll do something else. Okay, so now I want to clear some of what we're looking at. So I'm going to get a big old eraser out, and I'm going to get rid of this stuff. Yeah, get rid of all that. I'm going to get rid of this stuff down here too, because forget about decimal numbers. Binary numbers are cool. And I'm going to get rid of this stuff because we want to do a new number. Actually, maybe I didn't need to get rid of that. Maybe I could have just written the other one below. Yeah, maybe we'll do that. So what was it? 100101? I think that was it. I guess we could always check, but I'm pretty sure that this is the same as 37. And let's take a look at another one. So maybe let's go with, maybe a smaller number, something like 0, 0, 1, 0, 1, 1, 1. Yeah. Okay, good number. So what is this one going to be? Well, it's going to be a 16 plus a 4, which would make it 20, plus a 2, which would make it 22, plus 1. That should be 23. But let's find out. Let's make sure of that. So we'll say, let num be assigned the value of, what was it, 23? Is that? Yeah, 23. And then we'll return num.toString 2. Oh, case sensitivity. There we go. Now, this is actually a little bit different than what we were looking at. So notice how I had a 0 here, but I didn't put the 0 on this one. Well, there's a pretty good reason for that. It's the same reason I didn't put a 0 on here. Like, yeah, we know there are no hundreds. You would have written them if there were. So basically, the idea is that we don't need to write in this 0, but if you don't see it, assume it's there. Okay, that's the idea. I don't know why I undid that. Anyway, okay, so we're dealing with these two numbers, and now we probably understand binary, right? We're crushing it. We're masters of binary at this point. Okay, good. We're one with the bits. This is good. Binary is, you know, it's the true number system of computing, because that's what it's all based on, ones and zeros. And we can get more in depth in that, but maybe for now we'll just move on. So we've got these two numbers, and I guess I'll keep this stuff here, but I want to talk about bitwise operators. So I'm going to switch tools, to the hand tool. And say, okay, let's just scroll away from that for now. And we're going to do, actually, did I give that enough room? Okay, hold on a sec. Because I want to do something that we're going to be able to see from here, maybe. Yeah, it'll be fine. There we go. Okay, so here's what I want to do. I want to talk about these bitwise operators. So there are a few of them. Let's just say, first of all, that we're going to have two bits, and they're going to be called A and B. And we're going to look at a few possibilities. So A could be 0 or 1. And B could also be 0 or 1. So our possibilities is that A and B are both 0, A is 0, B is 1, A is 1, B is 0, or A and B are both 1. And we want to see what are the outcomes of our bitwise operators when we look at this. So the first one is kind of like an and I'm not very good at drawing ampersands, but not too bad. A and B. And you might be looking at this and thinking, in JavaScript, it takes 2 ampersands to say and. And yeah, good point. That's if I'm trying to say if two like logical statements are true, right? Did I use any here? Yeah, I did that, right? And. So that's a logical and. We're not looking at a logical and. We're looking at a bitwise and. Okay, so this might seem a little strange. So bitwise and is the same sort of thing, except it's taking that logic and applying it to these numerical bits, okay, binary numbers. The reason we can do that, and the reason binary has this kind of correlation to logic, is because logic is all about true and false values, right? Binary is all about zeros and ones. The two are kind of the same, you know? We just say false is 0, true is 1. That's kind of the way to think about it. So A and B, well, if they're both 0, then they're definitely not both 1. Because that's what it's looking for, right? Normally an and would say, well, it's only going to be true if A is true and B is true. So in this case, we're saying, well, it's only going to be 1 if A is 1 and B is 1. So if either of them are 0, we're going to get a 0. We're going to get a 0. In this case, and only this case, we're getting a 1. Okay, cool. So that's the way bitwise and works. Okay, and then we also have bitwise or, and very similar, and normally logical OR would have a double pipe. This is a single pipe, which is usually the key that's like, if you hold shift and press the button, that's above the enter key. But I don't know, maybe you have a different keyboard than mine. Point is, this one is basically going to say, well, this is going to give us 1. Sorry, let me back up. Normally, a logical OR would give us true if either the first thing is true or the second thing is true, or if they're both true. In this case, we're going to say the same sort of thing. So this will give us a 1 if the first thing is a 1, or if the second thing is a 1, or if they're both 1. So basically, we'll get 0 in this case because neither of them are 1. But in this case, the second one is 1. In this case, the first one is 1. And in this case, they're both 1. So we get a 1 from that. Cool. Now, we have this other thing, which is like a caret symbol. That's like shift 6 caret. You've probably seen that before. Some people use that to say like to the power of, like a to the power of b. This is what we used to use a lot. These days, it's more like a double asterisk if you want to talk about that. But anyway, point is, we've got a caret b. What could this be? Let me start naming these things. So this one was and, right? That was the bitwise and. This one was an or. And this next one, okay, this is maybe going to seem like a strange word. This is XOR, and the X stands for exclusive. So basically, unlike the regular OR, yeah, asymmetry, that is bothering me. Anyway, sorry. Unlike the regular OR, which is going to be, it's going to give us a 1 if the first one is 1, or if the second one is 1, or if they're both 1. This one, it's a little more exclusive than that. It's saying, I only want one of them to be 1. I'll give you a 1 if the first one is 1, or if the second one is 1, but not if both of them are 1. So we're going to get 0 in this case, because no ones. Here there's 1, 1. Here there's 1, 1. And here, they're both 1, so I'm afraid not. That's the X part of it. That's the effect of it. Okay. Sorry, it's bothering me how wobbly that looks. 1, 1, 0. Cool. All right, so these are our operations, our bitwise operations. So we could sort of put these to the test, but you might be thinking like, well, but what if my number isn't a 1 or a 0? What if it's something more complicated than that? I'm so glad you asked. So let me scroll this up for a sec. Okay. I don't know how we should arrange this. Maybe I'll do these down here. So I'm just going to copy these numbers, okay? So I'm going to say 1 0 0 1 0 1 and then 1 0 1 1 1. Okay, hopefully I don't forget those. Yeah, that's probably good right there. So what we want to do is some operations. So I guess we'll start with and, then we'll do or, then we'll do XOR. So what was it? 1 0 0 1 0 1 and then 1 0 1 1 1. I think that was it. Okay, so there we go. And for the first example, we'll say that this number is A, we'll say this number is B, and what we want to calculate is A ampersand B. I did a lazy person ampersand there, sorry about that. Forgive me. So we'll do our and the way it works up here. So basically we'll just look at like each pair of bits at a time, right? So just like we had over here, and maybe it's a 0 0, maybe it's a 0 1, maybe it's a 1 0, maybe it's a 1 1. But each of these are going to form the pairs that we're looking for. So let's look at those. So if we're looking at 1 1 and we want to do an and, then that will give us a 1. Okay, so that's good. If we're looking at this situation here, well, they're not both 1, so we get a 0. In this case, they are both 1, so we get a 1. Definitely not both 1. Not both 1. Not both 1. In fact, one of them doesn't even exist. But like I said, that kind of means that like there's this, no, I already used yellow. There's this kind of like implied 0 over here. Okay, so I'm getting 1 0 1. And what does that mean? You know, what's that telling us? Well, let's find out. So basically, we know that this number up here was 37. We know that this one over here was, what, 23, I think? And then this one, well, let's see, it's 1 1, no 2s, and 1 4. So it's 1 plus 4, which is 5. Okay, so basically what we're getting out of this is saying that 37 and 23 is equal to 5. Let's put that to the test. So let's just go back up here. I don't want to see that stuff down there, so let's just go with this, and we'll say return 37 and 23. And I haven't tested this, so I might be in for some embarrassment here, but let's find out. We're expecting a 5, but we'll see what we get. So suspenseful. Ooh, look at that. It's a 5. Cool. So I have to say, I've definitely talked to some people about this. I've encountered some people who have seen these things and just been so perplexed by them. Because, you know, you think and it's kind of like 37 and 23. I don't know. Do we add them together? Or do we get 60? And no, we get 5, which is like a number that's much smaller than these. So it seems kind of strange that we'd be getting something like that. But that's the reason. It's because of this stuff over here. Okay, cool. So that was fun, right? That was a lot of fun. So let's get rid of some of this stuff. Probably could have kept that. But I do want to get rid of this because I want to do another operation now. So instead of the AND operation, we'll do the OR operation. And therefore, we're going to be looking at this column here. So looking at these one pair at a time, we've got a 1 and a 1. So basically what we're checking for is, do we have at least one 1? Is there more? I'm trying to think of a way to say this with are there more than no 1s within the pair? There we go. Okay, so there are more than no 1s. So that's a 1. There are more than no 1s here. There are more than no 1s here. There are not more than no 1s here. There are no 1s. But we do have a 1 here. And we do have a 1 here. And keep in mind, like, even if we wrote in the phantom 0 there, it's not really going to make a difference. Probably eraser would have been more efficient there. Anyway, okay, so with our OR, we're getting kind of a larger thing happening here. So let's find out what that number is. We already know this is 37, this is 23, but what's this one? So it would be 1 plus 2 plus 4. So we've got 7 so far. No 8, but yes 16. 7 plus 16 would be 23. And then yes 32. So 55, I think that would be. I might be adding those up wrong, but I think that might be 55. Let's find out. So we'll put in the single pipe for that one. We want to return this, and we're getting 55. So again, seems kind of strange. This doesn't really seem like a math operation, but it is. It's a bitwise operation. Okay, so then what else is there to talk about over here? Well, I guess we've got one more operation to do, so let's do it. So yeah, it was this one. And this is, I think, the one that confuses most people because they're expecting it to do exponentiation. And it doesn't. So let's find out what it does do. XOR. So keep in mind, we want, we don't want there to be no 1s and we don't want there to be 2 1s. That's the idea. So we got 2 1s. Don't want that. That's going to be a 0. We have 1 1 here. That's good. 2 1s. No 1s. Also, this is good because it's got 1 1, and this is also good because it's got 1 1. Cool. All right. So, is that good? Yeah, I think. Did I do it right? Yeah, I think so. Anyway, okay. So, what number are we looking at over here? We have no 1s. We have a 2. And then we have no 4s, no 8s. We've got a 16. So we're up to a total of 18 plus 32. So that would be 50, I think. 50, which makes sense because it's missing this one and this one, which would be a total of 5 as compared to the previous one is what I mean. Okay, so caret. Run. So this, like if this actually was doing exponentiation, that would be just an exorbitant number, like probably more than JavaScript can handle. And we did get the 50 down there, so that's good. Yeah, it's not exactly integer material there. So that's why it's so shocking when you're expecting exponentiation to happen and you get this weird thing happening, like 50, that doesn't seem right. So that is something that has definitely perplexed many JavaScript amateurs. Okay, cool. So we talked about all the operators here. We've seen how they work on numbers. And notice that, importantly, we don't start with binary numbers. Like when we're doing these, they're written as decimals. So what's happening behind the scenes is it's kind of like it's converting each of these to binary numbers, like this. Then it's doing these operations, like whichever one of these, it's doing that on this. And then it's converting this back into a decimal number. I kind of doubt that's exactly, the process it's following, but it's doing something that's effectively what's the same result we'd get from that. So, okay, those are bitwise operators. Are there other bitwise operators? Yeah, there are a couple others. So there's one called not, and we're going to not talk about it. But what we are going to talk about is shifting, so left and right shifting, because we want to use that in this problem. So let's say we want to do something like 5, and we're going to left shift that by 1. So this is what the notation is going to look like. 5 left shifted by 1. Okay, it's kind of like this double chevron thing. Now, as we know, in binary, 5 is 101 because it's a 1 and a 4. Okay, so when we left shift it by 1, instead we get 1, 0, 1, 0. Because it's shifted all the bits by 1. It's just taken all of these, just shifted them over by 1, and now this is a 0. Okay, so this is 5 left shifted by 1. And what is this? So this is no 1s, it's a 2, it's no 4s, it's an 8. So 2 and 8, that's 10. So that happens to double the number. 5 left shifted by 1. There we go. It's 10. All right, and we could also do other things. Like we could do something like, I'll keep the 5 here just, for fun. Let's do 5 left shifted by 3. That should be kind of cool. So we start with 101, and we would get 1, 0, 1, 0, 0, 0, because we shifted it 3 units over. So when we look at this, no 1s, no 2s, no 4s, there's an 8, no 16s, there's a 32. So 8 plus 32, we should get 40. Okay, there we go. So it's kind of like we take the 5 and we're doubling it to get 10, then doubling it again to get 20, then doubling it again to get 40. We've shifted it 3 times. Now we can also shift it to the right. That's also possible. So if we wanted to shift this right 1, then basically we would have, it's getting kind of sloppy, sorry about that. Mouse writing, it's a challenge. We're right shifting by 1, so we get 1, 0. So that should really just be the number 2. So let's try that. Semicolons, very important. Yeah, we get a 2. Okay, cool. So, we can left shift as many times as we need to. Or right shift, it's whatever you want to do. But that's kind of like what we've looked at now. Wrong thing. All of this stuff, this is like, what you need to know about binary. Like these are tools that we're going to use for binary numbers. These are like our bitwise operators. So enjoy these, use them wisely. These are really, really sick tools. They can super come in handy. And I'm going to demonstrate that very soon. We're going to talk about this whole bitmask thing. Well, yeah, I guess we could talk about it now. Maybe we'll come back to it. So, okay, we've talked about bitwise operators. We talked a little bit about this Hamiltonian paths business as well, right? And we did get this to a point where we converted the problem into a graph. So now we kind of have a sense of what this bitmask thing is going to be about. We at least have all the tools ready that we're going to be using for applying our bitmask. And that's going to be pretty neat. But before we get into that, we've got to talk about dynamic programming. This is a really, really mind-blowing kind of thing. Like when I first learned about dynamic programming, I was like, what? You can do this? Like, it just seems like magic. So I wanted to show you some examples. So there are two examples that sort of come to mind when I think of dynamic programming. And one of them is, I'll call it the coins example. So it's like if you have, well, I'll show it to you in just a sec. And then the other one is called the knapsack problem, also known as the rucksack problem. And it's probably one of the most classic dynamic programming problems. So we'll look at both of those. Now, I was able to find the knapsack, or I guess backpack problem, or at least a variation of it here on codefights.com. This was from a while back. But anyway, we'll look at this one. This is going to be sort of the more complicated one. Dynamic programming can happen in 1 dimension or 2 dimensions. This is an example of a 2-dimensional one. So we'll look at this after. Now, I'm probably not going to be treating it exactly like the description because there's a slight variation on it. I'm going to treat it kind of like more like the classic version. But before we get into that, this is also a classic problem. I didn't make up this problem, but I couldn't find a task that was enough like it on codefights. So this one, like I did put this in manually. So in case you're wondering why it looks all sloppy, like it does look a little bit off-brand. It says task review up here. You know, I've got this like little edit button. There are no hidden tests on it. So that's because I made this one myself. But again, I did not invent this problem. This is a very classic problem. This is a known one that's been around for ages. And it's a really great example of dynamic programming. Or at least I think it's a great example of dynamic programming. Maybe you'll hate it. I don't know. We'll find out. But the main thing is, let's take a look at what it's asking us. So let's say you've got some coins of different values, and those are going to be represented by the values array down here. And we want to pay for something that's, it basically costs this amount, price. And so basically, if we're allowed to use as many of each type of coin as we need, like assuming we have infinitely many of each of these things, we want to find a way to pay for the item, so to cover the entire price of it, using the fewest coins possible. We want to minimize the number of coins. And that's really important. It's not that we're trying to minimize the value or anything like that. The value has to be 42, right? It has to add up to 42. It's the number of coins we're using that we want to minimize. So, okay, let's get into this one. So these numbers, I don't know how standard this is. I mean, this is kind of, this was like, these were the coins we used in Canada in 1995. In 1996, we got a new coin. By the way, in Canada, we call a $1 coin a loonie. So we got a $2 coin in 1996, and we call it a toonie, in case you're not familiar. I don't know in other nations what they do for currency denominations, but this is a snapshot of Canada in 1995. That's the idea. If it were now, there'd be a $2 coin, and there also wouldn't be a penny. We've phased those out. Anyway, okay, so we're going to start with kind of a brute force approach to this, right? We're just going to say, all right, we'll let coins be assigned the value 0. That's going to be the number of coins that we're going to use. So that's probably what we'll return at the end there. And then we'll just say, basically, here's my game plan. I want to go through the values array, but I want to go through it backwards. I want to start with 100 and say, hey, if you can drop hundos on this, drop as many as you can. And then from there, when we can no longer pay with hundreds, you know, when the price has been diminished to something less than 100, then we'll say, oh, okay, well, can we pay with 25s? And if not, or once we've done as many of those as possible, we'll try the 10s, then the fives, and then the 1s. So let's try that. So we'll say 4. Well, okay, normally I do something like, I don't know, let value of values, right? Because I'm not really intending to use the index of these things, but I can't really do that, or at least I don't think I can do that, because I don't want to start with 0. I want to switch it around. Now, I've heard there is a way of doing that with a for of loop, but it seemed a little, it seemed a little strange. It seemed like it was kind of not really more efficient than this will be. So I'll look into it more, but I heard from someone that we should expect something like that in ES7, but I really have no idea when ES7 is going to be. But it'll be exciting. Anyway, the point is, so value is the value. So it's going to start at 100. It's going to start at 100, go to 25, 10, 5, 1. And notice we're starting at length -1, because the length, like this would have a length of 5, but it doesn't have an index 5. This one would be index 4. And then we're saying while I is greater than or equal to 0, because there is an index 0. It's just if it goes below 0 that it's going to become a problem. And very important that we put a minus in here. If we didn't put in the minus, if we made it a plus, then this will never finish, because I is never going to be less than or equal to 0. It's starting as a positive number, it'll never make it to the negative. So notice we get an execution time limit exceeded. On test 1, in particular, it doesn't make it any further than that. Okay, so great. We've got our minus. That should at least complete. It's obviously not going to pass the test because 0 is going to be the value of coins. We haven't altered it at all, but it should at least complete. It shouldn't time out this way. Okay, so what we want to say is while price is either greater than or equal to the value, then we'll say, first of all, price minus equals value. We're going to take away that value from the price, and we're going to say coins plus, we use the coin. So we're going to add one on. And let's just tighten that up a bit. If you're wondering about this here, or why it's a while, basically the idea is, if we take a look at a test here, yeah, that's a good example, I guess. So on this one, like we could drop 4 of these loonies on this, right? And then it would get down to 20, and then we'd say, oh, okay, can we do any quarters? No. Any dimes? Yeah, 2 dimes. So it's not just an if that we want to do, it's a while, so that it goes through all of them and really spends as many as it can. So let's try this. Now look at this. It worked for 5 out of 6 of them, but it didn't work for this one. Let's try to figure out why that was. It actually failed pretty colossally. It's saying it would take 12 coins, and really the answer should be 6, or at least it's saying it should be 6. Let's verify. So if we had to pay for something that costs 60, and we have denominations of 1, 10, or 31, yeah, I think I would just spend 6 of these. I think that would be the least number of coins possible. So, what's going on with this one? Well, basically it's saying, is 60 greater than or equal to 31? Yeah, it is. So then it subtracts the 31 from that, and then we get 29. So we'll drop a couple 10s on that, but then it's down to 9, and all we have left are 1s. And it's going to take a whole bunch of them. It's going to take 9 1s. So that's not great. That's not, that's not good. So it's not passing all the tests, even though it's passing most of them. So, you know, if we're dealing with 1995 Canadian currency, no problem. This algorithm is sufficient. It'll work. But if we're dealing with, maybe this is like Canada 2159 currency or something like that. I don't know. The point is, this is going to be a little different. This algorithm isn't going to work as well for something like this. So, enter dynamic programming. What we've done so far is not dynamic. This is just, you know, there's some chump change over here, excuse the pun. So let's get this out of here. No. That's a comment. Okay, so actually, I don't even want to see it. I'm sick of looking at that. Okay, so here's what we want to do. We're going to make a new array. This is the idea behind dynamic programming, and we're going to use DP to represent dynamic programming. So this is going to be our dynamic programming array. And the idea is that dynamic programming is a strategy that we can use when we're trying to solve a problem which can be broken down into overlapping subproblems. Let's unpack that. So what I mean by that is dynamic programming allows us to move through an algorithm without repeating calculations. So every calculation we do, we're going to store it in an array, and then we're going to use that value. We're going to just look it up in the array instead of recalculating it any other time that we need to use it. That's the idea. Okay, so for this one, we're going to do a for loop. And we'll call it n, actually. So n in this case is going to represent the price. And that might seem a little weird because we sort of have the price already. So the way this is going to work is, it's funny because like hearing myself describe this, it sounds like it's super overkill. So instead of just calculating how many coins we would need to minimize the number of coins we'd have to spend on something that costs 60. Instead, we're going to find the minimum number of coins we have to spend on something that costs 0, 1, 2, 3, 4, 5, 6, 7, all the way up to 60. So that's what this array is going to be storing. We're just going to be storing all of our values. So we're going to say, okay, what's the minimum number of coins for something that costs 0? Oh, 0? Oh, okay. Well, what about for 1? It's got to take 1 coin. Okay, what about for 2? 2 coins, etc. Well, okay, and we'll see how it builds it up, but that's how we're going to do it. So I'm going to say let best be assigned the value of 0. And this is going to be the value that we're eventually going to be pushing into our array. And then basically at the end, let's do this for now just to show the whole array. But really, we're going to want the last element of it because that's the one that's actually going to cost 60 or whatever the actual price is. Notice n is going all the way up to and including price. Okay, so all right, let's do this. So basically, the idea in here is we want to say for let I be assigned the value of 0, I is less than values dot length, and values at I is less than or equal to n. And I'll talk about why that is in just a sec. But before we do, we'll do the contents of this loop. So first of all, we'll say let value be assigned the value of values at I. Oh boy. Okay. Too many usages of the word value in there. But anyway, coins. Coins is going to be the number of coins that we have to spend here. Okay. So coins is going to be this. It's going to be 1. Okay, so this is the coin we're spending right now. This is the additional coin. And we're spending this coin in addition to the number of coins that it took to pay for something with a value of n minus the value of the coin that we're spending. Okay, so like, for example, we're going through this loop, and if we get to a point where we find that it's like, let's say n is like 7, okay? So n is 7. We've got up to the point where n is 7. So that means we already have done 0, 1, 2, 3, 4, 5, and 6. Okay, so the way this is going to work is it's going to take the values and it's going to say, well, we could use a value of 1, right? So if we use a value of 1, then the number of coins it's going to take is 1 plus however many coins it took to pay for something that costs 6, right? Because we're at 7 right now. So to pay for 7, we could spend a penny plus however many coins, the minimum number of coins that it takes to pay for 6. Okay, or we could move on to the next value and say we could pay with a 5, and then it's going to be 1 coin still plus however many coins it takes to pay for something that costs 2, because we're subtracting the 5 from it. And then basically the idea is we want to say, well, if best is 0 or if coins is less than best, then we want to say best is coins. Okay, so the reason I'm saying this one over here is just in case it's already set to a 0, like we don't have a best, or if coins is actually a lesser value. Best here means the minimum, right? That's minimum possible number of coins. So we want it to be smaller. And so if it is, we'll say best is coins. And then best is the thing we're going to push in there. So let's run this. And this is not a lot of code. This isn't like longer than what we have down there, or, you know, marginally. But look at this. This is something. This is pretty interesting, actually. In fact, let me make this more readable. Let's throw a dot map on this, and we'll say coins and price. So coins are the actual value here, number of coins that it takes. And then price is, well, the index, right? Because that's what it was. Pay for something that costs 0, pay for something that costs 1, that costs 2, that costs 3, all the way up to 42 in this case. So we'll make this a string, and it's going to say, want to buy something, wait, okay, here, want to spend, this is better, price, question mark, I'm gonna need coins. Okay, so that probably looks a little weird because I'm doing some weird concatenating and stuff like that. So, want to spend 0? Gonna need 0 coins. Want to spend 1? Gonna need 1 coin. And I could have done an optional S on that, but yeah, who cares? Anyway, here's where things get interesting. So if you want to spend 4, yeah, you're gonna need 4 pennies. But as soon as we get to 5, now it's just 1. For 6, it's gonna be 2. For 7, it's gonna be 3. And then once we get to 10, back down to 1 because you can pay for it with a dime. So isn't this cool? This is dynamic programming, and like, look at all the data we're getting from this. This is amazing. And notice the last part of this, like, is the actual question, because it's saying price 42. How many coins do we need? And when we get to the end, want to spend 42? Gonna need 5 coins. And that's the answer. It's what we're looking for. That's kind of cool. So instead of returning this, I'm actually gonna console.log this, yeah, all of that. And then after that, I'm going to return the final element. So I could say, like, you know, dp at dp.length -1. And that should give us the final element right there. And hopefully it's the correct answer. Look at that. It's passing all the tests, including this one. So if we have these weird coin denominations, we find it kind of goes up in a weird way. 1, 2, 3, 4, 5, 6, 7, 8, 9, back down to 1, up to 10, back down to 2, up to 11, back down to 3. But then when we get to 31, it causes a strange rift in it where we're back down to 1. But anyway, the point is, dynamic programming is a lot like magic. It can be a bit tough to understand, but once you see the trick behind it, it's very simple. By the way, there's another way we could do this, and I don't know which is better, because I feel like this one, it needs to get the length of it, but we just do this, dot pop, because it's going to be the last thing at the end of the array anyway, so we can just pop it right off of there. And there we go. Okay, so that still passes all the tests. So that's dynamic programming. It's cool, right? Isn't that cool? I think it's pretty cool. All right. That was a one-dimensional example. And I don't mean by that it was, like, you know, flat or boring or something like that. I mean, literally, like, the array we were working with had just one dimension. It wasn't like a matrix or something like that. But as I mentioned before, dynamic programming can happen in more than one dimension. We can have two-dimensional dynamic programming. It's a thing. And we have an example of it. So I guess we'll wrap up with this one. Now, unfortunately, I guess you're not going to be able to like interact with my solution here. You know, you're not going to be able to, like, you know, go on here and click my name and stuff like that. So sorry about that, but you can look at this. I mean, soak it in. Pause the video if you have to, because I'm about to switch away from this. So hopefully you enjoyed that. Let's take a look at our two-dimensional example now. So this is the backpack problem. We're talking about a thief who has a backpack that can carry exactly Gmax kilograms. he can stuff it with the items he found in the house he is burglarizing. This is a dark question. Only whole objects can be put into the backpack, so they cannot be divided into pieces. For each object, you know its weight and price, and those are represented as arrays. So we have a weight array and we have a price array, and basically like they line up. So the first item would have a weight. The first item would have a weight of 80 and a price of 8. The second one would have a weight of 10 and a price of 20. Okay, so that's basically how it goes. Or I guess instead of the first and second, I should have said the 0th and the first, but you know, that's getting a bit pedantic. So our task is to find the maximum profit the thief can make. That would be a silly question if it was the minimum. Like, don't do it. Or better yet, if you're looking for maximum profit, there's probably better ways than burglarizing a house. Anyway, the point is, it's not meant to be an ethical question. It's meant to be a programming question. And so, actually, I mean, this is one of the most classic dynamic programming problems. It's one that you tend to see a lot. And so, it's a good example, but there's one thing I don't like about this particular variant of it. And it's this last line here. I don't like that. Notice that the weight of all objects in the backpack must be equal to G max. I don't really care for that variation. I would say it's got to be less than or equal to G max. Because otherwise we get into these weird situations where like, oh yeah, and there's also the case that maybe dude can't get any items, in which case -1. There was one of the tests here. Was it the first one? Oh, I guess it was. Okay, so 29 struck me as a bizarre value for this, because if we can carry 100, then that means, let's see, if we want some of these big ticket items, we can get 30 from this 31 here. What else can we get? We can get 20 from this 10 one over here. And we could get another 20 from the 55 because, you know, 10 plus 30, that would be 40 plus 55, that's 95. So we could get a total of 20 plus 30 plus 20, so 70. We could get 70, does it say? I'm assuming these are dollars, but, and yeah, the weight is in kilograms, so technically that should be called the mass. Anyway, speaking of pedantry. Okay, so basically what I'm trying to say is if the burglar keeps his pack a little lighter and only carries 95 kilograms instead of the full 100, then he could get away with $70. But instead he's settling for 29 just because he's such a stickler for filling up his pack. I don't support that, so I think the answer here, in terms of the way I'm going to do this, the answer is going to be 70. Okay, so sorry, it's not going to match up. It's going to look like we're not actually passing all the tests, but we will. Maybe, you know, if we do a good job, I guess. So let's give this one a try. Now, like I said, this is going to be a two-dimensional dynamic programming situation. So specifically, it's going to be kind of like a matrix where each of the dimensions is going to sort of represent something different. Okay, so the rows of our matrix here. Let me draw a quick matrix just so we have something to look at, a visual to go off of. So yeah, this is not a nice looking matrix, but that's okay because it's going to get the point across, I hope. Anyway, the point is, like we were looking at in the previous one, remember we were looking at the coins problem, and we found that when we were looking at that one, we really just wanted to know how much it was going to take to pay for something of the specified price, right? Like, or cost. It was like, it costs 42. How many coins do you need for that, right? And instead, the way we did it is we said, okay, well, what's the minimum number of coins that we need for 0, 1, 2, 3, 4, 5, 6, like everything all the way up to 42. So, oh no, my stream buffer's a lot. Oh, damn. Sorry to hear about that. Okay, so set the quality to 720. What's it set to now? I'll have to look into that, but thanks for bringing it to my attention. Okay, so, all right, for now, we're looking at this matrix, and the idea is that we want the rows to represent something and the columns to represent something. Now, in the previous one, basically, for the columns, we were sort of, like, we got our final answer in the last one, but everything leading up to that sort of helped us find that. And so we sort of, even though we knew the price we were looking for in the last one, we still did a whole array of all the prices leading up to that. We're going to do something kind of similar to that in this case, except the difference here is that it's going to be this. Gmax is the thing that we're going to be looking at on the columns. So basically, we'll say, like, well, what if Gmax is 0? What if Gmax is 1? What if Gmax is 2? All the way up to, you know, whatever it's supposed to be, like 100 or something like that. Okay, so then that's what this dimension is going to represent. Okay, so each row is going to have all the possible values leading up to Gmax. Okay, and then the columns here are going to represent sort of like the objects in play, right? So okay, this is like if we're only looking at object 0. This one would be like if we're looking at object 0 or 1, or object 0, 1, or 2, all the way up to however many of the objects there are going to be. So like n. And maybe I should have used different colors for those, but oh well, that ship has sailed. Okay, so that's basically what we're going to be looking at. We want to create a matrix, so two-dimensional array, where each row is going to be an array containing the set of all results for various Gmax values, specifically corresponding to just the objects that we would have on that row. And that's now that I'm repeating that, it does seem a little complicated. So maybe let's actually get into the algorithm and see if that can help us make better sense of it. We're going to start the same way as last time. We're going to start with just a dynamic programming array, and it's going to be empty. And it's the thing that we're going to be returning, but not really, because we're actually going to be looking at some particular value of that. Now, first thing I want to say is if we're going to have no objects, you know, if we're going to have no objects in here, so starting at 0, there are 0 objects, we'll say let 0 row based on the value of this empty thing. And then basically the idea is we're going to fill up the 0 row with zeros all the way up to Gmax. Okay, 0 row. And this is the sort of thing that's really a lot easier in some other languages, but it's worth it. We heart JavaScript after all. Okay, so there we go. So right now it's just gonna have a 0 row. I guess I'll just return that just to convince you. There we go. A whole bunch of zeros. Definitely a lot of them. Way more than we're kind of expecting to see here. It's going way off the page, but yeah, that's fine. Okay, so then we've got our 0 row. Great. Now we want to iterate and look at all the other rows. So if we have, I'll say n. Yeah, n for like number of objects. N is going to be 1 to begin with, because we want to go from 1 all the way up to the, oh, no, we've already used n. We can't use n again. We'll just use I. Yeah, because we used, we'll just use I. All right, here, we'll use row. No, we've already used row. Oh man, I wasn't expecting this part of it to be so complicated. Anyway, here we go. That's fine. We'll use I. It's different from this I here. They're block scoped. Nothing to worry about. Okay, so for let I be assigned the value of 0, I is less than or equal to ni plus plus. And we're going to fill up a row. So we're going to say let row be assigned the value of that. Oh yeah, we didn't already use row. We used 0 row. Okay, we're using it now. And then at the end of this, we're going to dynamic programming dot push row. Cool. Cool, now we just have to fill up the row. So we're gonna say for let, I also say like cap for capacity. Cap is going to start at 0. It's going to go all the way up to and including Gmax, and it's going to go up by 1 each time. And then we're going to do something sort of similar to what we had before, and it was this. So we're going to say let best be assigned the value of dynamic programming at I minus 1 at capacity. So basically, I'm just saying, like, yeah, now that we can look at, okay, so if we're comparing it if we're comparing to the 0 row, right? This is just all zeros. And then we're saying that's for if we have 0 objects, if we're, not looking at any of these. And then we can say for the first iteration of the loop, so I is 1, so now we're looking at having just the first item here, right? So basically, okay, the reason I'm saying this best is dp at I minus 1 cap is because I minus 1 is just like the previous row, and capacity is like which spot are you looking at, right? These were all of our capacity values all the way up to G max. So, but that's not the only possibility. Like if the capacity is greater than or equal to weights at I, yeah. If the capacity is greater than or equal to weights at I. So that means, do we have room? Like, will our capacity permit this object to be packed inside the backpack? So if that's the case, then we're going to say, oh, okay, well, then in that case, best is going to be math.max of best, what it was up there, or dynamic programming at I minus 1 at capacity minus weights at I. Okay, so first of all, what is this? What are we talking about over here? Well, it's kind of like what we were saying before with the coins. This is the part that tends to be a little more confusing, but just like with the coins, we were saying, if you're going to spend a nickel, then you're going to spend 1 coin plus however many whatever the ideal number was for something that was this value minus a nickel, minus 5 cents. So in this case, we're saying, yeah, it's the same as what we had on the previous row. For a capacity that was the same as this capacity minus whatever the weight of this object is. So in other words, we're saying, okay, take off the 80 or the 10 or whatever it is, and then with the remaining capacity, what was the ideal value that we could get out of that? Because that's what we want, but that plus values, or I guess they're called prices in this case, prices at I. Okay, so it's still the same I as this. We're talking about the same object. So 80 and 8 are that's if I is 0, if I is 1. We've got 10 and 25. And I'm just realizing now, even though it sort of makes semantic sense for this to go from 1 to up to including n, I'm just going to make it do this, because that way the I is actually going to represent the object itself. And that means this needs to not be a minus 1 anymore, because there's already a 0th row when we look at this the first time. When I is 1, there's already going to be like a first row available in the dynamic programming array. Okay, this is a bit messy. Here, let's do it like this. Let's say I'll just say alt for like alternative, and we'll just put this up there. Oh, I could probably spell alternative. That's better. Yeah, that's better. That's nice. Okay, so there we go. Don't like it when it splits onto the next line. That's gross. Okay, so then here what we want to do is row.push best, whatever the best ended up being. And it's got maybe a bit of breathing room there. Yeah, that's a bit better. Okay, so basically the best starts out as just whatever it was on the previous row. And if it turns out that we can handle the object in there, then we'll say, oh yeah, okay, well, if the previous one was better, then we'll go with that. But otherwise, we'll go with this alternative, which is basically like the value that we get from this object plus the optimal value that we would get from something that had a maximum capacity of the current capacity minus the weight of this object that you're adding to the pack, so like the remaining capacity. Okay, So is there anything left to say about this? Let's try running it. We're going to return the whole dynamic programming array. Okay, didn't have an error, so far so good. And now this is getting a little chaotic. There's a lot of stuff here. Really what we want to do is we want to say that all of the objects are involved, everything right down to the final I, and that we're talking about the full capacity G max. So we want to go all the way to the right. And we find, oh, look at that, 70. Geez. There we go, 70. Well, that sounds a little familiar. That was the value I said I was going to find for this one. So, nice. Okay, whereas in this case, it's all zeros. We can't get anything out of this one, which is why they're encouraging us to return -1. Okay, and then this last one over here, or is it the last? No, there's another. We should get 150. Let's see if we're getting the 150. Yeah, we're getting the 150. And the reason we get the 150 for this one is because when we fill this thing up, we're going to be able to take, I'm pretty sure, all of these objects. Yeah, because 10 and 40 is 50, 20 plus 5 is 25, plus another 25 is another 50, which gives us a total of 100. So it fits perfectly, which is, you know, like we were saying, that's what they want. That's got to be exactly equal to Gmax. But that's not really, as far as I know, I don't think that's really part of the traditional 0-1 backpack problem. So that's why I didn't really bother with that too much. Yeah, the 1, there we go. NBD. All right, cool. So that was fun, right? That was nice. I guess if we wanted to make this more proper, we could say something like dynamic programming at n and Gmax. Wait. Oh, right. Case sensitivity. There we go. Gmax. Is that right, or do I have to do any -1s on that? Yeah, there we go. So we get the 70 on that one. We get, well, at 0, we really should have -1. We get 150. Could I just do something like this, I wonder? Or -1? Would that at least appease the second test here? Yeah, it would. So we get a -1. And the reason that works with the or is because if this is 0, that's typecast to false. So it says, oh, well, better check this one. It's a -1. Okay, go with the -1. So that's pretty neat. I've definitely seen some people who make really good use out of the double pipe here, like using logical ors and stuff like that for just really neat stuff I wouldn't have thought of. So keep in mind, these ands and ors and stuff like that are not necessarily just for like ifs or like whiles. Like it's not necessarily just if you're trying to do Booleans. There's other stuff you can do with them. Now, whether that's considered hacky or like an abuse of notation, I'm not really sure. You'd have to ask someone who's more of a JavaScript guru than I am, I guess. Anyway, that's that. Yeah, that's the backpack problem. Anyone have any questions, comments, concerns, suggestions? Well, it's just about that time, I think. If we go back to what our friend Zero Cool had to say over here, we were looking for a dynamic programming algorithm over a bitmask. And we had this time complexity, which was a lot better than the other time complexity we saw. So hold on a second, take a sip of water and then I'll resume. Okay, that's better. Sorry about that. I've been talking for 2 hours straight. So, okay, let's see. We've talked about dynamic programming. We've talked about bitwise operators. We haven't totally talked about this bitmask idea, so I guess we should. Yeah, I guess we should. So when I'm talking about a bitmask, what I'm trying to say is if we take a look at like, you know, what the problem's asking, we've got these things here. Now, this blew my mind, I have to say. Like, I was already impressed with dynamic programming. I was already on board with dynamic programming. It's I think it's awesome. I think it's magical, in case you couldn't tell. But anyway, I was already really convinced, and you know, it was at a point where, like, I guess I was becoming a little desensitized to it. I wasn't really quite as amazed, I guess, with all the dynamic programming problems I was looking at. But when I saw this one, I mean, Words can't describe it. This was a transcendental experience. And the reason is this. So you know how we've been talking about how we can use, like, let me just make a little more space here, how we can have like a two-dimensional, actually let me make a lot more space. Let's get that out of the way. Let's really clear the field here. And I will keep the description there for now. So, okay, here's what I want to talk about. So get a good color up in here. And now, okay, we're going to have a matrix. So I want to get that nice visual back in here. And we sort of need to think about how we're going to break down this problem into a set of overlapping subproblems like we did with the previous ones. Oh, wow, that's not even close to being a straight line segment. Anyway, like for example, in the coins example, we said, like we broke it up into subproblems that were based on the price of the object, right? So we said, well, if the price is this whole thing, well, we worked up to that, right? So we said, okay, what if the price is 0? What if the price is 1? What if the price is 2? All the way up to the actual price we were looking for. In the backpack problem, we broke it up in 2 ways. We said, well, on this axis, we'll have the capacity, which will go all the way up to G max. On this axis, we'll have the objects we're including. And it was basically just like, okay, we'll start with none. Then we'll start with element 0. Then we'll start with elements 0 and 1. Then we'll start with elements 0, 1, and 2. In this case, it's not going to be quite so simple. And the reason I say that is because we don't know which direction our Hamiltonian path is going to be going in right off the bat. We don't know if it's going to be going like this, or maybe something totally different than that. So our Hamiltonian path, it's not going to be as predictable. We're not going to be able to just as easily say like this one, then this one, then this one, then this one. Because like I said, you know, what if it was a case like this, right? Where we didn't have that. So we can't just say it's 0, then 1, then 2, then 3. You know, we've got to think about this differently. So we're going to do this on the basis of subsets. So we'll, you know, like maybe it's 0, maybe it's 0 and 1, maybe it's maybe it's 0, maybe it's 1, maybe it's 0 and 1, maybe it's 2, maybe it's 0 and 2, maybe it's 1 and 2, maybe it's 0, 1 and 2, maybe it's 3. And in case it's not familiar what I'm doing there, and I totally wouldn't blame you if that doesn't seem familiar, I'm talking about binary numbers. What I'm talking about now is a bitmask, and I might as well just use this page to sort of sketch this out. Let's say, what goes good with green? Oh, lavender, of course. All right, so let's move that guy down there. Cover up that little question mark. So, okay, here's the idea. When we're talking about numbers, we'll start with decimal numbers. So for decimal numbers, we've got 0, 1, 2, 3, 4, 5, 6, and 7. Okay, so we've got those, and now I want to represent those in binary. Now I know from last time that I shouldn't use that butter popcorn color, so I'm going to use kind of like a burnt umber, or maybe a terracotta. So this one is just going to be 0 in binary, just 0. This one over here is going to be 1. 2 in binary, well, that's 1, 0. 3 in binary it's a 1 and a 2, so it looks like that. 4, well, that's just 4. It's 1, 4, no 2s, no 1s. 5 is a 4 and a 1. 6 is a 4 and a 2. And 7 is all 3 of these things. Okay, so what I'm talking about here is basically where the idea of a bitmask comes into play. And I guess I'll just do one more here. Yeah, just one more. Oh no, where'd my lavender go? Here. So there's 8. Cool. All right, so these are binary numbers, but basically what I want them to represent is this. So this column represents whether or not we're including the 0th element. This means we're including element 1. This is for element 2. This one is for element 3. So we're talking about subsets, right? This is an empty subset. This is the subset containing just the 0. This would be the subset containing just the 1. This would be the subset containing the 0 and the 1. This one over here, just 2. So, and it goes on from there, right? Until we get to this point, which is just going to be 3. And it would go on from there, right? We'd have like 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, you know, like it goes on and on. The main thing is that we're going through these and we're representing each of these subsets as a binary number, which can in turn be represented as a decimal number, right? So basically the idea is a bitmask is allowing us to represent a subset of elements from the array using only a single number, which is beautiful. What a beautiful idea, because normally like that would be so big, you know, compare it to this. And I'm going to use a color that I hate because I hate this. So let's say empty array. This is the array containing 0. This is the array containing 1. This is the array with 0 and 1. This is the array with just 2. This is the array with 0 and 2. This one's 1 and 2. This one's got 0, 1, and 2. So like the idea is this over here, gross. Oh God, I didn't think that was gonna happen. But this stuff over here, good. Good. I approve. Okay, so there we go. Great. So that's a nice visual just to show, to show that when we're talking about a bitmask, it's a way of representing a subset of elements using just one decimal number. Isn't that cool? Oh man, I think that's so cool. All right, so that's what we're going to be doing. That's actually what we're going to do over here. Oh yeah, that was a straight line, wasn't it? Definitely PogChamp worthy. Okay, so basically the idea is this. In this case, yes, we're going to do our dynamic programming. And again, each of the axes here, each of the dimensions is going to represent something a little bit different, right? So basically, when we're talking about this one over here, like this is going to be for basically the length of the array. How many elements are we using? And actually, well, okay, it's not how many elements are we using. It actually represents something a little bit different, but each of these is going to represent one of the elements. So it's going to be like a 1 and then a 2, a 0 and then a 1 and then a 2 and then a 3, etc., right? All the way up to however many there are. This side over here, this is going to be our bitmask. Oh, that's pretty fast writing for a mouse. Anyway, so this will be 0, 1, 2, 3, 4, 5, etc. But again, we're thinking about these not in terms of the numbers they actually are, but in terms of more like what they represent. These represent sort of like our subsequences. Sorry, not our subsequences, our subsets, right? So going back to this one over here, like we're using these numbers, but we're using them to represent these actual things. And in fact, even more than these, because we're not just talking about like the indices and not just 0 and 1, 0 and 1. Like we're actually talking about having like ABA, BBB, like those are the things that would be in the array here actually. So like this is a huge savings. Like we're really economizing a lot by just using single decimal numbers for each of these things. So really I want to emphasize like no good. Okay, so cool. So this is like this axis here is representing which elements of the array we're including within our subset. What this one is going to represent over here is the following. Okay, so this is going to be a matrix containing either true or false values. Okay, so it's going to look something like this to begin with, and then false everywhere else. And we'll talk about why that is. So what each of these true and false values represent is the following. Okay, we'll take this one, for example, right? So first of all, we have 3 here. So as you remember, that would be equivalent to having the 0th element and the first element in our subset. So if we have just this one and this one, so ABA, BBB. Okay, so that's what we're talking about. If we have just a subset containing those elements. And then specifically, I was saying we're looking at this cell, right? So in this cell, the reason this is false is because there is not a Hamiltonian path that ends at element 1. What we're saying over here is if we're talking about a subset that contains only the first element, then there is, or sorry, the 0th element, then there is a Hamiltonian path that ends at element 0, and it's just element 0. So we're using a large matrix here of just true and false values, and what each of those represent is whether or not this subset, or the subset represented by our decimal numbers down here, contains a Hamiltonian path ending at this element. That's the idea. Okay, so that's how we're going to do this stuff. That's the game plan. Anyone have any questions? I realize it's like kind of complicated stuff, especially if this is your first time seeing dynamic programming, and super especially if it's your first time seeing a bitmask or like bitwise operator. So like I'm throwing a lot at you. I realize that. I guess, yeah, if you're watching this live, feel free to ask a question. If you're watching this on YouTube, feel free to rewind or ask a question, put it in the comments or something like that. People have done it. It's worked out great. Okay, so awesome. Let's continue. Let's actually implement this thing. I'm dying to make it happen. This is going to be so much fun. Okay, so let's get rid of that. Sorry to see that straight line go. But yeah, okay. Actually, I didn't need to do that. I could have just kept that there. Oh well. Okay, so oh yeah, we definitely don't need this anymore. Actually, I'm really glad we noticed that, because if I'd forgotten about that, remember, a return basically stops the function. So I have a feeling I would have been like running the test and being like, why is it just giving me the number 2? I don't get it. Anyway, okay, glad we avoided that potentially embarrassing situation. So let's get a couple of values in here. Okay, so we're going to say constant length is assigned the value of input array dot length, and that's also going to be the length or the number of rows in our matrix, in our dynamic programming matrix. We're going to say width is 1 bit shifted length many times. So actually, maybe we should talk about that. What does it mean to bit shift 1? Well, basically a 1, if we think about it, and oh yeah, I'm already on the hand tool. Cool. So a 1 is, that's just 1, right? So if we bit shift 1, how many times? How many times do we want to do it? 3 times? Is that enough? Okay, we'll do 3 times. So if we do that, then basically 1, well, we start as 1. And then we shift it over, so it becomes 1, 0, 0, 0. Okay, so what is that? Well, no 1s, no 2s, no 4s, but there's an 8. So it's 8. Okay, so this was just equal to 1. This is equal to 8. It's not a coincidence that 2 to the power of 3 is 8. Okay, so, I mean, the main thing is that I could have written this a few different ways. Like, check it out. I'll say return width, and then, oh yeah, I did tell it to run the test, but I can't find the tests. Oh no, I'm gonna have to reload the page? I'm missing the tests. Oh no, there we go. Okay, great. So, what am I returning here? Oh, I'm already returning edges. Forget about that. We want to return width, so we can take a look at that. Oh yeah, I got you, Firefly. I've got all those in a playlist in case you haven't seen it on YouTube. You're probably aware of it. Okay, so return width, so it's 8. Okay, but we could also just say like math.how 2 to the power of length. We should get the same thing, right? 2 to the power of length is also 8. Or we could even take advantage of some of that fancy new ES6 notation and use the double asterisk to exponentiate it. And we're still getting 8. So like there are lots of ways of doing this. I'm gonna do the bit shift method because it's nice, right? It's a new thing that we're learning about. It's fun, it's interesting. We have an understanding of it, having spoken about it over here. So basically, yeah, the width is working the way we want it to. Now, why is the width that? You know, that's maybe a question we should be asking. Why are we using 8 in this case? Why are we using, what would it be in other cases? Still 8, just 4 over here. Well, it's for our bitmask, right? So we need to know where we can end this thing. We basically, if we have 3 elements, we need to get to a point where we have like all ones, right? 1, 1, 1. So that would be 7, which is 8 minus 1. And so, you know, we'll do like in our loop, we'll say something like our iterator is going to be strictly less than width. So it's not going to get actually all the way to 8. It's going to be less than 8. So we'll stop at the 7 here, which is just what we want. 1, 1, 1. Perfect. And, you know, like we saw, if it was one that only has 2 elements, then we'll do 4 minus 1, which is 3, which will just be 1 and 1. Okay, great. That's as far as we need to go, because we only need to go as far as the point where we have a subset that contains all 3 of the elements that we're looking at, or all 2 of the elements, or all 4, you know? So like, that's why it's kind of like a power of 2 minus 1 that we're going to be going up to. Okay, so that's width. That's going to be the width of our dynamic programming array. Speaking of which, let's get that up in the mix. There we go. And let's see. We want to do a loop that's going to fill this thing up. So I is 0, I is less than length, which we've defined above, I plus plus, don't need that extra space in there. And okay, so what do we want to put in here? We want to basically say, okay, we'll let our row be this empty thing, and eventually we're going to push that into the dynamic programming array. And let's see, what do we want to be doing in here? Well, basically this, we'll say for let j be assigned the value of 0. I mean, it's a 2-dimensional thing after all, so it makes sense to have 2 iterators. J is going to be less than width. So like I said before, it's strictly less than. So if width was 8, this is only going to go up to 7, which is good. It's what we want. Okay, and then we're going to say row.push. What are we going to be pushing into row here? Well, basically this, what we want to say is if j, okay, let me put it this way, all right? Anytime we bit shift the 1, okay, so 1 gets shifted, in this case 3 to the left, there's just going to be just 1, 1. Everything else is going to be a 0. If we were to shift it like, I don't know, like 1 time to the left, then we're just going to get 1, 0, still just 1, 1 in there. We could shift it like, let's say 5 times, and then we'll have 1 and then 5 zeros. The main thing is that there's always going to be just a single 1 in here. So if we're talking about this in terms of our bitmask, that means we're just looking at just one of the elements. That's the idea. So if that one element happens to be the element we're talking about here with I, well, then we should put it true, because that would mean the bitmask is basically saying that if we're dealing with a subset that just contains that one element, like if we were to say, hey, this 1 here, is there a Hamiltonian path that ends here? Well, yeah. This is it, you know, it's just that element itself. We've visited every node. We visited it, yeah, it's up here, right? A Hamiltonian path is a path in a directed and undirected graph that visits each vertex exactly once. So we're doing it, you know, if this is the only vertex we're looking at in our subset, then yeah, we visited it. We visited it exactly once. So we're good. Okay, cool. Sorry about the train noise there. Hopefully that's not too loud. Okay, so what do we want to say here? Well, I guess I'll just do something like this. Okay, how about this? We'll say if j equals 1 shifted I many times. Yeah. If j is the same as basically taking a 1 and shifting it left I many times, then that's the situation we're talking about. We're talking about a single element, and we're obviously going to have a Hamiltonian path. So, okay, I'll do it something like this. So I'll say row.push true. And otherwise, row.push, false. And I'll just comment this one out for now. And are we doing a return on that? No, we are not. Let's return that dynamic programming array and we'll see what we're getting. Look at that. Just as prophesized, it's something that looks like this, where the true is here, the true is here, the true is here, and then it's false everywhere else. And the reason we have trues in here is because these just represent the Hamiltonian paths that are just one element. So, you know, this would be, okay, let me mark this up a little bit. Yeah, that's good color. So this would be 0, 1, 2, 3, 4, 5, 6, and 7. So as we saw in binary, you know, 7 is the one containing all of them. That's like our 1, 1, 1. And reflect that down here, I guess. 1, 1, 1. The 6 would be our 1, 1, 0. The 5 is 1, 0, 1. The 4 is 1, 0, 0. The 3 is, I guess, I'll put the leading 0 even though we don't need to, 0, 1, 1. The 2 is going to be 0, 1, 0. The 1 is 0, 0, 0, 1. Sorry, 0, 0, 1. Well, yeah, I guess it's also 0, 0, 0, 1. But anyway, the point is this one's 0, 0, 0. Okay, so in terms of our subsets here, this one contains no elements. This one contains only the 0th element. And so, yeah, there's a Hamiltonian path ending at the 0th element in a subset that contains only the 0th element. This one contains only element 1. And so, yeah, there's a Hamiltonian path ending at element 1, but not element 0, not element 2 or anything like that. And then the only other true is for the one that contains only element 2. Okay, so this is looking good. I like our matrix here. It's looking nice. The reason I commented this out and instead of just, you know, deleting it altogether is because look at this. With this if statement here, we're kind of saying like this thing, if this is true, then push true. If this is false, push false. So why not just push that thing itself? Because we already know if it's going to be true or false, right? The only way we'd get to this is if it's true, and the only way we'd get here is if it's false. So we don't actually need to do all that if business. We can keep it a lot tighter by just doing this. Row.push j equals I shifted left, 1 shifted left I many times. Same thing. Great. That's what we're looking for. Okay. We're almost there. I'm so excited. Oh, this is going to be fun. So this, I would say, is kind of the probably the trickiest step we're going to have to do. Got it. There we go. So yeah, we've done a lot already, but this is where things get kind of tough. So first of all, what we're going to do is we're basically going to go through all of our binary numbers. Okay, so I'm going to say for let bin for binary be assigned the value of 1. I'm going to start at 1 because there's not really any sense in checking what would happen for a subset containing 0 elements. And then I'm going to say bin is less than, I guess, width and bin plus plus. Yeah, cool. That's what we want. So this is sort of going through all the binaries, all the different, you know, possible values for our bitmask. And then we'll say let indices be assigned the value of. Okay, so here's what I want to do. I want to take our numbers here, like our binaries, and I want to change them into the actual indices that we're looking at. So the way we're going to do that is going to be like maybe a little strange, because basically if we have a binary number and that binary number is like, I'll say 1 0 1 0 0, for example, that would be for like a bigger, let's put another 1, that would be for a bigger one, you know, like a larger set of elements. But we could have that, you know, like we could have 10 elements here, so it's definitely fully possible. And I mean, 2 to the power of 10, that's, what even is that, like 1024 or something like that? I don't know. I'm bad with numbers. Anyway, the point is, this would be our binary. This is like our bitmask. But what we actually want is an array that would contain the indices for the elements. So like this is saying that like the element with index 0 should be in there. So index 0, yeah, be in there. The one with index 1, no, don't be in there. The one with index 2, don't be in there. The one with index 3, yeah, be in there. But not index 4 and yes, index 5. So notice how this is kind of similar to this, but number 1, it's an array. And number 2, it's kind of like flipped around. So that's what I'm going to do. I'm going to say that this is going to be bin dot toString. Oh, that's weird. I was expecting an autocomplete. toString, and something we've seen before actually. toString with a base of 2. So that's going to represent this as a binary number in the form of a string. And importantly, since it's a string, I can make an array out of this. So there are 2 ways to do that. I could do dot split, which is basically going to split it up at every blank string, which is in between every character. But I don't actually really like to do that, especially if we're talking about a case where we're not going to use the corresponding join. So instead I'm going to use array.from. And that's going to do the exact same thing, except it makes a little more sense to look at, I would say. You know, it's clear to me that this is going to give me an array, whereas the word split doesn't really communicate arrayness. Okay, and then I'm going to do a dot reverse on the end of that. So that's just a built-in for arrays, just a quick little useful for checking palindromes and stuff like that. But anyway, why am I doing reverse? Well, I reversed it. We took this thing, we flipped it and reversed it. So the 1 went over there, the 0 went over there, this one went over here, that one went over there, and so on and so on. So that's why we do a reverse on that thing. So that's going to give us our actual indices. Now, why do I want them to be reversed? It's basically so that as I'm going through this, as I look at an index, I can just say, okay, indices at I. Is it 1? Is it not 1? You know, nice and simple. Okay, instead of having to do something like, you know, with bit shifting or something like that. Anyway, it's just a little easier this way. For let I be assigned the value 0, I is less than length I plus plus. Okay, if indices at I is 1, so in other words, with this bitmask, okay, with this binary number, we're wondering, well, as we're going through each of the arrays, it's length, right? Which is, sorry, each of the elements of the array, not each of the arrays. As we're going through each of the elements, we want to say, well, is this one being included in the, in this subset? Is this one of them? And if it is, then we're going to do something real neat. Okay, so, oh boy, here's what we want to check. So, I need a diagram for this. I need a visual. So let's go over here. And okay, let's say that we have a set of nodes, okay, a graph. So there's a node, maybe we'll do like 5 nodes. I don't know. Yeah, probably 5 nodes is good. And then in terms of the edges, let's say we've got this one and that one. And this one, that one, and I don't want like a full star here. I'll just do something like that, I guess. So, okay, first of all, is this one where there is a Hamiltonian path? Let's see. Boom, 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 boom. Yeah, there is. Okay, so there's at least one Hamiltonian path. Now, what I'm trying to say is I'm going to use this as a way of checking to see if there's going to be a Hamiltonian path. I'm going to try to relate it to the problem so far. But before I do that, just want to give a quick peace out to Firefly7. Thanks for watching. Glad you approve. I approve of you being part of the audience. Stop by again sometime. Bye. But not bye to the rest of your viewers. We're going to keep going with this. Okay, so let's say, and this is sort of like the inductive nature of dynamic programming, right? We use induction. So in other words, we're kind of building up on stuff that we already know about it. We're not repeating calculations. So basically what we're trying to say is this. Let's say we've already looked at a subset of nodes that's like, let's say these 3, okay? We already have looked at that one. And we already know that there is, let's say, a Hamiltonian path that ends at this element right here. Okay, that's the idea. So then what we want to do is we want to check a new one. So we want to say, okay, now we want to look at this one. We want to know, well, like, can we include this? Is this one going to have a Hamiltonian path too? So we just go through all these others and we say, well, is it connected to one? Is it connected to a node that has a Hamiltonian path ending at it? And if we look at it, it's connected to this node, but that one doesn't have a known Hamiltonian path ending there. And this one doesn't have a known Hamiltonian path ending there. So we'll say, no, that's going to stay false. Whereas when we check this one, we say, well, okay, let's see. This one doesn't have a Hamiltonian path ending there, but you know what? That one does. So this one would sort of get like a true. And that's how we're going to build it up. So that's why we're concerned about whether the Hamiltonian path ends at that particular node. You know, like the whole thing where we were checking that, where we were saying like with this stuff, you know, like, or no, it wasn't this stuff. It's when we were looking at the like X value, so to speak, in the matrix. Like, here, let me run the tests again, which I guess I'll have to pull up from here. That was very sensitive. Okay, so yeah, basically we're talking about this, right? So what I'm saying is for each of these rows, is there a Hamiltonian path ending at element 0 among the subset of elements for each like value of the bitmask here? And really what we're looking for is to see if we can finally get to the end and have the full set of elements that we're looking at here and actually have a Hamiltonian path ending there, because that's really what we want. We want to have a Hamiltonian path. Now the reason we want to find one that's like ending at 0 or ending at 1 or ending at 2 is so that we can actually use this to build up to the next Hamiltonian path, which will now end at this one, so we can put a true in the matrix there. So what this boils down to is there are basically 3 things that we need to check. Okay, so first of all, we're saying this index is included here. So we're going to compare it to all the ones that it's joined to. The way we're going to do that is we're going to say for let j be assigned the value of 0. J is less than length, j plus plus. So also going through all the nodes of the array, or the elements in the array. And I'm going to say if, first of all, I is not equal to j, just like we had upstairs, right? Yeah, over there. So that's the first thing, if I is not equal to j. What else do we need to check? Well, we need to check if indices at j is equal to 1. And that's basically just saying, well, is that element also in the subset that we're looking at? I didn't really mention that here, but, you know, we could have said like, you know, maybe there's like a phantom node over here that we're just not considering yet in our subset. So we would say, don't compare to that one. Okay, so it needs to be one that's also in the subset. What else? Well, okay. It has to be joined, right? So edges has to include I, or sorry, edges at j has to include I. So in other words, edges at j dot index of I is greater than -1. And this is getting a bit long here, so let's just pop these onto the next line. And we'll have another and, which we'll put onto the next line. And this one, I would say, is kind of going to be the tough one. So we're going to say dynamic programming at j, and then something else here. So, okay, let's just remind ourselves of the things we needed to check. We needed to check that both of the elements we're looking at, so like this one compared to this one, we need to check, are they the same element? No, they're not the same element. Okay, are both of them part of the subset? That's what this one is saying. Yeah, they're both part of the subset. Okay. Are they connected? Is there an edge between them? And that's what this one is saying. And yeah, there's an edge between them. But then the key thing is there a Hamiltonian path that ends at this element? And how do we know? Well, that's what our dynamic programming matrix is doing. So is there one that ends... okay, is there one that ends at element j, which involves a subset So bin, that's like our subset with all these elements. But really what we're trying to say is not for one that has all 4 of these elements. We want one that just has these 3 elements, the ones we started with. So we basically need to say, well, we want something that doesn't include this one. So let's say this. Let's say, for example, we have like 1, 0, 1, 1, 1. Okay. So what number would that be? That would be 7, not 8, but yes, 16. 16 plus 7 is 23. Oh yeah, 23. We saw that one earlier. Okay, so that was 23. That's like the bit number that we're getting up to. And then we'll say that this one is, I don't know, element 2. Okay, so we'll say that, that it's this one over here. So we could do something like this. We could say, okay, we'll say 0, 0, 1, 0, 0. So this right here is basically like 1 bit shifted I to the left, or like 2 to the power of I or whatever it is. But it's basically 1 and it's been shifted, in this case, 2 times to the left because it's index 2 that we're talking about. Just, arbitrary example, but we'll just put a 2 there. Okay, so then for this, the idea is that we want something that's going to have this, have this, not have this, have this, and have this. So that's an exclusive OR situation, isn't it? Because really, I mean, that for XOR, which maybe we'll remind ourselves of XOR. Where was it? It was over here somewhere. Yeah, XOR. So that's what we had over here, actually. And what we found is the only time that we're going to get 0 is either if they're both 1 or if they're both 0. So if the 2 are like, matching elements. So over here, we would get a 1 here. We'd get a 1 here. We'd get a 0 because those are both 1s. We'd get a 0 here, but that's good because it was a 0 to begin with. And we'll get a 1 from that one. So check it out. Basically, what happened is we took this thing, this bitmask, this representing a subset, right? So it's saying, yeah, we've got elements with indices 0, 1, 2, and 4. And now we're saying, okay, but I don't want the one containing all of those. I want the one that's just containing 0, 1, and 4, let's say, right? So that's what this is going to be. And the reason I want to compare to that, which is, by the way, I guess 19, because we're subtracting 4 from it, but let's verify. So 1 plus 2 plus 16, yeah, it's 19. Okay, so we're instead going to look at 19 because we're going to say, well, what I wanted to know is there a Hamiltonian path that ends here? Is there a Hamiltonian path that ends at this element when you're just considering these 3? And then we'll bring it into these 4, we'll bring the 2 in, and we'll say, well, yeah, if there was a Hamiltonian path when we were looking at the subset of these 3 and it ended here, now we can extend that to this one, which we know is in the subset, which we know has an edge to this one, and we know that it's not the same as this one. So that's the thing we need to check. We need to do this XOR with a bit shift, 1 shifted I to the left. So that's what we're going to do. Bin is what we were starting with, and we'll do an XOR, and we'll do a 1, not 11, 1, that's the double tap I wanted, I. Cool. And just to remind you, we are in the middle of an if statement here. It's a pretty massive if statement, but it is an if statement nonetheless. And if that's true, then we want to say, well, dynamic programming at I, at bin, it's true. We can extend the path to go all the way to this new element. Cool. Okay, so then let's see what that's looking like now. So this one, does it look any different? Yes. Yes, it does. Not much different, but a little bit. If we look at this one, yeah, it looks quite a bit different. We actually have some trues at the end here. And if you think about it, that's what we want. I mean, okay, basically A, B, 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 A, A. This is funny. We're coming full circle now because this was one of the first things I did in this problem, but I'm going to redraw it. So I'm going to say A, B, B, and A, B. Okay. So then we'll use another color for the edges. So these two don't have an edge, but these two do because they differ by 1 character, and these two do because they differ by 1 character. And what was the indices on these things? It was, no, that color's not going to work. let's go with, yeah, like a brown. Yeah. Okay, cool. So AA was 2, BB was 1, AB was 0. Okay. So basically that means there is a Hamiltonian path here that ends at 1, and that same Hamiltonian path happens to also end at 2. That's really important because that's what this is saying, right? There is one at 1, it ends there, and at 2, it ends there. And keep in mind, like this column here is the one that represents the full subset of elements, all of them. Okay, cool. So that's what we're looking for. That's why we should get a true for this one, whereas we should get a false for this one, because there's nothing in the final column that had any trues on it. This one, no trues, should be false. This one has trues, should be true. This one, huge, but doesn't have any trues, so should be false. This next one, also huge. And it looks like it should be true. That means it's got trues at the end. It's got 2 of them. Okay, cool. So we're just about done. What we need to do is to say, let's just search this last column here. We'll just search that. And if we come across anything in that last column that's true, then we'll return true. So we'll say for let row of dynamic programming array, we'll say if row at width minus 1, because keep in mind width in this case, and not width, it was like 8 in this case, but we want the element with index 7. Okay, so if row at width minus 1, oh yeah, we're talking about the row. I was going to put a second index. Yeah, row at width minus 1. Return true. That means we found it. And if we didn't find it, let's return false. So, okay, let's just clean this up a little. Want to make it look nice and presentable for the big run here. Okay, I think it's looking good. There's a lot of stuff here, but let's give it a run. Well, that feels good, I gotta say. Okay, so are we ready to officially submit it? And I'm gonna just get a bit more space here because we'll know if it passed or not. So, so many fond memories here. We were so young. All right, let's submit this now. And beautiful. Doesn't that feel great? And in the time it took us to come up with that second algorithm, somebody else actually completed the problem. So that's pretty cool. All right, so there's a lot here. There's a lot here. Yeah, there's a lot here. Like I said, I was surprised that this one worked. And in fact, okay, I don't think this emote was really accurate. I think it should have been more like one of these because it wasn't even necessarily a pleasant surprise. It's kind of a bittersweet one, to be honest, because I almost kind of wanted to have like a reason to want to go through all this. But of course we do have a reason, and it's the joy of learning and the joy of conquering a problem like this with such an optimized, beautiful algorithm. And so let's see. Okay, let's go over here and let's check the comments here again. Let's see what our friend was saying over there. So, yes, 0 cool. This page helpful in developing a dynamic programming algorithm over a bitmask in big O of 2 to the n squared. Okay, great. So that's it. That's what we've got. So let's say that. Great algorithm. Big O of 2 to the power of n. Maybe I'll like extra bracket this. Yeah, maybe that's best. Or okay, here, I'll do it like this. 2 to the n times n to the power of 2. Is that a palindrome? Oh my. That is something. Okay, so just when you thought that this task couldn't get any deeper, goes and throws a palindrome at us. Okay, very cool. Well, I don't think there's anything left to be said for this. I think we covered all the bases. Really long algorithm here, really complicated, but really beautiful in how it gets the problem done. I mean, really, it's economizing a lot because it's not repeating calculations that it doesn't have to. And I mean, yeah, that's just a beautiful thing. I'm happy with this. I think you should be happy with this too. And well, I mean, you know, for yourself is what I'm trying to say, because you have the power of bitwise operations. You have the power of dynamic programming on your side now. You're going to be unstoppable with these new abilities. So I guess that's it. Yeah, we submitted it, right? Yeah, we submitted it. And actually, I don't know if we submitted it with the comment over here. And let's get a legitimately very happy face there. Okay, so we'll submit that officially, and that'll tell us which number it is. It is solution number 3685. So click on that after you complete the problem if you want to take a more detailed look at this. And let's see, maybe just to finish up, for anyone who's, you know, watching on YouTube or something like that, I'll just sort of show this one bit at a time, just, you know, in case it's hard to see the whole thing at once. So this was our function that checked to see if our strings actually did differ by 1 like we wanted them to. This was our edges. So this is basically where we converted this problem, the strings problem, into a graph. And then this is where we started our dynamic programming matrix. This is where we loaded it up with just the singletons, right? The subsets containing only one element. And then this is really where the magic happened, right? This is where we sort of increment through and get the extra little bits of the calculations that we need to keep extending it out to the boundaries. And then this is where we say, okay, well, did we make it in the end? Did we get to a point where we found that including the full set of elements within our subset, we were able to find a Hamiltonian path that ended somewhere? And if we don't find one of those, that's when we return false. Okay, so that's basically the whole algorithm. If anyone has any questions, comments, or concerns on anything we covered in this incredibly long video, let me know. Pop a comment down below or whatever. You can also contact me on Twitter. I guess we'll finish up with this. So yeah, nice job, everyone. Great job. Okay, so next time will be